I'll introduce myself. So welcome everyone to a tutorial on neural net verification. Today, myself, I'm Ekaterina Komendantskaya. I work in Heriot-Watt actually and Southampton in both universities. Luca there is from Birmingham, and Daggitt, who will join online. He's now in Japan. He's here in Heriot-Watt University, but he's starting a prominent position in Australia very soon. So one thing to say, the tutorial is called not vehicle, but neural net verification and with vehicle. So actually, as you will see from the tutorial, my goal is to discuss with you what this area is about, where it's going to, where it should be going to, and only as a secondary goal also to learn the tool vehicle. Talking about the tool, so we have a team, and this is not a team of all the people who contributed. This is the team of people who contributed to the tutorial slides specifically, or tutorial materials. So people we should really acknowledge would be Matthew, who you will see today, and Van Kokke there. So they are two main developers. They are real hands and brains behind vehicle as a tool. While Natalia is doing, well, you will see basically, I think pretty much every person you will see cited in one or the other of the papers that support vehicle. But some of them do theory. For example, Bob Atke does type theory behind it. Natalia does theory behind learning functions. She's a PhD student. Ben is our MSc student who contributed some materials, etc. Mark, who does natural language processing. So different people do different things, but two main developers, Matthew and Van, should always be acknowledged when we talk about vehicle, of course. Okay, so what I was trying to do, what we'll try to do in the next 20 or so minutes, is just to give a gentle introduction to neural networks, even for those people who never trained them or never really used them. And set up notation that we will need throughout the tutorial. Well, what is a neural network? We usually think that there is some input data, and sometimes it's images. It could be actually any data you can imagine, but whatever data it is somehow then converted to either vectors or matrices of real numbers, rational numbers, sometimes even binary numbers. It depends what the type of your input is. Then this input, sanitized somewhat compared to your initial data, is given to the neural network that has the same number of input neurons, we call them, or the same size of the input layer as the size of your data. Then this data pass through the network. When you see an arrow, it usually means that there is some number associated to the arrow by which you multiply the value that comes from the input. When you see several arrows come to the same neuron, that's a sum, so they're summed up, and then they're brought like this forward to the network. And finally, there is some final neuron that gives you some kind of an answer. So in this case, it says, yeah, I think what you've given me as this data is number 5. I will not talk about training too much now, but of course, to make this actually a good classification and to get to number 5 out of this data, there's training going on. We'll come to this in the second half of the tutorial. But for now, let's just assume it's some kind of static function by magic, able to classify for us the data we throw at it. And it does so by basically multiplying and adding different numbers that we pass through the input, and the output somehow can be magically interpreted as a class 5 in this case. What we really need to remember, and we'll be using this, is the neural network formally is a function, and well, this Rn to Rm, I specifically don't use R for reals because sometimes we'll be using reals here, sometimes rationals. But it's from usually either from reals or rationals, and they're from vectors of reals to vectors of reals, or respectively rationals.
What's the rationale for using a rational?
Yes, because the solvers deal with them more easily. Okay. Yeah. And constructive theorem provers as well. So reals open up the whole can of worms when you go to constructive theorem proving as well. All right, so neural networks are ideal for what we call perception tasks. They approximate functions when exact solution is hard to get. They are tolerant to noisy and incomplete data. But of course, they also bring up some other problems. Solutions are not very easily conceptualized. Even in my little example, it was very difficult to understand why exactly all these multiplications and sum give me the right answer. They're also prone to a new range of safety and security problems. such as adversarial attacks, which we'll mostly be talking about in this tutorial, but also others like data poisoning, catastrophic forgetting. But let's have a look at the adversarial attacks, since it's going to be one of our iconic examples of problems that arise in neural networks. So this is an image. I trained my neural network to recognize images of digits, and my neural network is happy to classify this as a 0 with very high confidence. And then I apply a little bit of noise. Well, to us it's a visible noise, but actually once you apply this mask to the 0, it's going to be looking exactly like my other 0. But suddenly the neural network predicts that this is a 5, and not just predicts it's a 5, but in this particular experiment, its confidence was 92%. So this is a classic example of adversarial attack, and this is what we dislike, right? Actually, when machine learning community brought up this example, there was such a shock. And when I was reading this literature, that why were they shocked? Because they knew that the neural network never give us exact solutions. There's always an approximation and optimization. And the shocking bit for machine learning community is a lot of claims is coming to the fact that, oh, our neural networks becoming intelligent. They are surpassing human ability to recognize something. And of course, this example challenges this thesis, right? If the neural network that was classifying with high confidence this as 0 was really understanding the concept of a digit, of course it would have given the right answer on the right as well. It's because it has no clue about the concept of a digit, it can make the mistakes like on the right. That's why it causes such a huge uproar, because this challenges the very hypothesis that machine learning is learning concepts rather than just does optimization. But anyway, there are more bad news about this. So the perturbations usually imperceptible to human eye. So if you do implement it on some kind of device, you wouldn't even know that something goes wrong. Attacks transfer from one neural network to another. So if I found this 0 on the right that can make my neural network vulnerable, with high probability I will be able to attack with the same image your neural network. And also you could say maybe it's only for images, but they literally affect any area where you apply neural networks. You may be recognizing natural language or other kind of inputs. You will always be able to craft some kind of adversarial example. From that to verification property. Very often when people talk about the previous kind of problem, they like to conceptualize this way. So they say, well, technically, if we wanted to say my neural network is robust to attack, well, I could say, for example, this. So suppose this is my 7, of which I'm sure of. And then I'm imagining there's a set of perturbation of my 7. And the set of perturbations is by drawing some sort of epsilon ball around it. Actually, mathematical definition is very simple for epsilon ball. Epsilon ball for my iconic image x hat, it's my central 7, and an epsilon is defined as a set of all vectors in a space of my input, such that those vectors, difference between those vectors and my iconic image x hat is less than an epsilon. So the definition of epsilon ball is very, very easy. Yeah, and then I'm saying, well, what I want to say for my neural network to be robust, it means that within this input space, within this epsilon ball of my iconic image, everything else should be classified as 7. Okay, you can perturb this 7 in any way you like, but I really want to ensure that everything inside it gives the right class. And we will actually see that there are many ways in which we can define this robustly, classify all points within Bx robustly. There are some choices how to do it. So I choose to keep this slightly informal for now, but we'll massage this problem in a few ways today. Is everyone happy with the epsilon ball robustness? Okay, so just to give you a little bit of a variety, another iconic example in neural net verification is this ACOS-XU challenge. ACOS coming from some aviation standards in the United States, and so the example comes from there. So it's a real-life implementation, real-life example. So a neural network is trained to take 4 inputs. And the first element of the vector will stand for distance to intruder, the second angle to intruder, angle-intruder heading, speed, own speed, and intruder speed. So these will be the vector of size 5 that will be given to the neural network. And the neural network will need to give us a few outputs. It will say clear of conflict, strong left, weak right, strong right. So it's basically collision avoidance system, but implemented as a neural network. The story, and yeah, so all these parameters are here. So if this is our shape, then theta, angle to intruder is measured here, rho, distance to intruder is there, own speed, intruder speed, and then this angle there. So a bit of a history out of interest. So the system was initially implemented as a 2 GB lookup table where all this information was given. If the speed is this, go there. If the speed is that, do that. But then it was replaced with a neural network in order to improve size and latency requirements. This was done, the publications concerning this application of neural networks and verification of that neural net were in 2017, so it's now quite some time past. I think that's an important example because even now you often see when you talk to industries, they tell you this story. They say, we used to have exact calculation of this. We replaced this with a neural network because it's faster, it's more convenient, or simply because my boss likes neural networks. But once you do this, of course, you want some safety requirements because neural networks are not guaranteed to give you the right answer. Then ultimately someone comes and says, well, then you please prove those few properties about the neural network. And in the case of ACAS-XU, engineers gave 10 properties. And this is an example of what they formulated. That's property 1. So let's have a look at it now briefly, and then we'll come back again to ACAS-XU properties as an example in the next lecture. So as an example, if the intruder is distant and is significantly slower than the own ship, the score of clear of conflict advisory will always be below a certain fixed threshold. Okay, so if the speed is fine and distance fine, please don't bother the system with false alarms. And moreover, this is kind of said in English, and then engineers who were implementing this air collision avoidance system also could actually give some numbers to this. They said, well, the angle should be greater than this, and speed should be greater than this, and that own speed should be this, and intruder speed that. And in this case, that's the score of clear of conflict. So usually, and this is common in industrial verification of neural networks, engineers who implement that neural network are able to massage down and give you those magic numbers, of which as a computer scientist who implements this, you have no idea. You just take this for granted that these are good numbers. And more generally, the way the area is developing now, given a neural network with the type from Rn to Rm, verification of such functions most commonly boils down to specify admissible intervals to the function's output, given an interval for its inputs. So you've seen for epsilon ball, we're saying that's admissible input interval, give me that output. And for ACAS-XU, we were also saying, okay, for these particular values of the vectors bounded like this, could you give me the output of certain kind? So just a little bit of a context where this all started and where it's heading. We generally distinguish the period between 2011 and 2015 as the time when people were just trying to understand that they kind of first found this problem with adversarial examples and were trying to understand, is it a major problem, what's going on? So there was actually a very first verification tool in 2011, but it was still a niche. It didn't really get many users. These papers were very influential in 2013. That's when machine learning community said something's wrong with neural networks. We should do something about it. And after 2013 until 2015, machine learning community started to massage this problem down, finding examples in different domains. And so for real, it's in 2017 with Guy Katz and this example of ACAS-XU when we really have the first neural network verification for real. And the tool Marabou, suggested by Guy Katz and his colleagues, is still on the market and we still use it. In fact, today in the exercise session, you will use it. And then since then, there are dozens and dozens of publications, different kinds of verifiers, approximate, complete, based on abstract interpretation. So if you were in 2017, pretty much Marabou by Guy Katz would be your only choice. If you just go now and Google neural network verifiers, you'll find hundreds of papers, and it will not be that easy for you to decide which one is better, because many of them will claim victories on the battle. Okay. So if we were to divide, somehow make sense of all these verifiers in terms of what kind of technology they're using. So Marabout, the very first one, used SMT technology, so it's SMT plus domain-specific algorithm for processing ReLU networks. Then Iran is abstract interpretation-based. Yesterday we had Infro that was using some of abstract interpretation ideas, so this is very similar, I guess. Whenever you go to some verification domain, some ideas will be replicating themselves. There is VeTSS that uses interval arithmetic, and Alpha Beta Crown, which is a winner of competitions on neural net verification for a few years, uses linear bound propagation. The area, because it's booming area, but it's also young area, it was a big deal to start developing international standards for neural net verification, which were supported by holding competition VNN. So this site VNN-lib.org would guide you to annual competition on neural net verification. As usual, competitions usually lead to standardization, because if you want to judge people competing against each other, then you need to have some kind of standards that they all follow. Okay, Marabout is our choice in vehicle and in this project that we're all participating in, because it gives a richer language for us to work with than other verifiers. And also it's complete. So let's talk about the life cycle of neural network verification. As we've seen, those ACOS, GZU engineers, other engineers left us with N properties and say, please make sure that your neural networks satisfy those properties. So we have that nailed down very quickly. Well, I may want to do some training for that property, right? I know my neural network is not robust. So usually very first thing what you find out is that your neural network does not satisfy that property, like we did with MNIST. You don't need to ask me whether the neural network that I've shown you robust or not. I've given you an adversarial example. It means the neural network doesn't satisfy the property. So very first thing is to do training to encourage that property within neural networks. Perhaps I want to do counterexample search, so the finding adversarial example was exactly that exercise that we've done at the start of the lecture. So there are a few algorithms, PGD, FGSM, that will find adversarial examples for you given a neural network. Maybe I will straight away run verification with Marabout or Iran or any other tool I want to use. And then very often I will need to integrate that into larger properties about the systems. Very usually my neural network is part of some larger system, and so I need to think how to incorporate the guarantees I've given possibly here about my neural net into guarantees about larger system. And there's some interaction between them. So training might depend on counterexample search, because if I found a counterexample, I may as well inform training with the knowledge of that counterexample. Of course, sometimes counterexample doesn't find something, but verification gives me counterexample, and then I may also feed that back to training. Are we all okay with this as a large scheme of things? Any comments or questions? Okay. The area has several challenges. This is my take on this, but maybe other people have slightly different opinions. I think it's pretty much what is a consensus. So first is the theory. So finding appropriate verification properties. We know about ACOS GZU example. We know about robustness as a verification property. But in general, it's not so easy to find even what we want to verify. So you're given a neural network that recognizes something, and then go and find out what you want to prove. So that's not easy in the general case. Solvers. So there is a problem with undecidability of nonlinear real arithmetic if you wanted to use neural networks with real vectors. And of course, scalability of neural network verifiers is a problem as well. SMT solvers initially were not built to work with that huge number of parameters as neural networks hold. On the machine learning side, there are also problems in understanding and integrating property-driven training. So how do we for an arbitrary property, how do we encourage a neural network to satisfy that property, what it means for geometry of the spaces that we are trying to classify. For programming, finding the right languages to support these developments. And finally, for complex systems, integration of neural net verification into complex systems is also a very big problem, and I don't think it has been really successfully resolved as yet. Some of these problems are aggravated by insufficient programming language or API support. So let's have a look. So if today you just wanted to honestly verify a few of your neural networks, you go and dig down the code, and this is one. So this one is for training. You give a property and then it trains for your property. You try to read this code, and everything is mixed in one large bag. So, for example, can you guess what property this is encourages for? Well, I guess there is a title, robustness constraint. Well, also you could, by the fact that someone using epsilon rather than some other notation, you might say, well, it's probably epsilon ball. But apart from the title and the eps here, it's very difficult. There are some batches, there is some clipping. The pre-processing and post-processing of data is mixed with property statement. And if something goes wrong with this and you need to debug it, it's actually very, very difficult. You don't know whether your property is not holding, or maybe something happened on the stage of this clipping, projection back to your input spaces. So not easy. Well, there is this tool art, abstraction refinement training. So this would be, again, because they were good enough to use ACAS, you'd probably say, well, that's ACAS XOO example. Otherwise, if they use some less suggestive names, you will say, well, okay, well, at least they plugged in some numbers here. Well, new low, new high, but again, difficult. You cannot see the property stated in one place so that you could say, well, I do trust that property or not. This is Marabou. Well, with Marabou, at least there is some discussion here in the header that there is some kind of normalization of vectors. So between the time that the engineer gave us those magic numbers and the time we implemented neural networks, something happened with the input and we need to normalize it. But then it kind of starts working with normalized numbers straight away. And so we're losing a little bit the connection between what engineer asked and what we asked the neural network to do. This is Iran. So if you are just given this, you don't know, is it a ACAS XOO or something else? It's very difficult to interpret these files at all. It's very strange for you to work with. And if something goes wrong or the property says, no, it's not satisfied, you wouldn't know where to start. This is VNN-lib. That's the standard for neural network verification. VNN-lib, if someone knows SMT-lib, how many people know SMT-lib? Okay, so SMT-lib is a standard for SMT solvers. If you wanted to encode something in SMT solvers, you'll use this. VNN-lib basically uses SMT-lib plus some of the conventions for neural networks. So this is not too bad, but again, you don't really see this is an ACAS XOO property, and this is an input given by engineer, and this is normalized input. Also, the bad thing about this, I'm not like this and etc. The problem with this, well, maybe you'll tell me what the problem with this is. So this is for ACAS XOO. What would happen if I started to write MNIST specification in this style? MNIST image is 28 pixels by 28 pixels. So yeah, several hundreds of inputs will be written like this. And MNIST is the smallest examples. They're easily images that have thousands of pixels. So it's strange. And the files look huge. Yeah, not ideal, but probably best of what we have. And in fact, Vehicle, which we'll be talking today about, will be compiling down to this standard. But at least it will not ask the user to deal with this. So looking at these existing literature on neural net verification, we could perhaps narrow down to a few problems. What we found was the problem. So the first one, interoperability. Properties are not portable between training, counterexample, and verification. Some tools do one, some another, and with this awful syntax, it's very difficult to understand how to merge this together. Next is interpretability. code is not easy to understand. Forget that we don't have a good connection between training and verification. Just looking at the code sometimes is difficult, and writing this is difficult. Integration. Properties of networks cannot be linked to logic control system properties, because if they're written in a very low-level language, almost at the level of let's work with these vectors of for input and that for output, it's very difficult to reason about large systems in vector terminology. And the final one is embedding gap. There is little support for translation between the problem space, as the engineer gave us, and input space, the vectors as we implemented them in the neural networks. And very often there is some gap. So the tool vehicle is designed to address all of these 4 problems. So vehicle will look like this. It's a domain-specific functional language for writing high-level property specifications for neural nets. So again, we assume that someone has given us the magical property. Then something that we're adding and that hasn't been present in the previous literature would be this analysis and informative error messages. It's not just that we put this in a high-order language as a property so that humans could read this, but also we could give some support for the user in case something got wrong in the spec. So there is these 2 blocks cover both the language syntax and type checking and compilation. But then obviously you need to do something. It's not just enough to say your spec is type checked. Congratulations. You need to do something in practice. And so very first thing that we did, of course, with vehicle is we made sure that we can compile down to Marabou and run Marabou from vehicle. But that's, of course, not enough. We also need to compile down vehicle specifications into training. And training often depends on counterexample search. And wouldn't it be great to also integrate this all into high-order provers? And in particular, what we have done is AGDA integration. So Matthew is going to show today how he integrates this to vehicle. Crucially, this is all the lower part of this graph is done automatically. So as a user, you only really need to specify property in vehicle and care that it's type checked and it's nicely written. Everything else, this kind of dirty work, low-level work with vectors, will be done by the compiler. So that's vehicle's philosophy. As it happens, other people were thinking about better APIs for neural net verification, so we were not the first, fortunately or unfortunately. So there is a tool called Socrates, written in Python. Given a specification and a network, it calls different neural net verifiers, because if we have hundreds of neural network verifiers, why don't we ask all of them to solve the problem and then see who comes up with the solution first? Like Georg showed us yesterday, right? He calls from Isabel and several SMT solvers compete in solving that problem. So that was the idea. Unfortunately, it left unresolved all of the 4 problems that we talked about: interoperability, interpretability, embedding gap, and integration. So none of this was solved by the tool. It was simply to call many verifiers in the same style as before. Then there was Never 2.0. It was building upon Socrates, but also added training, pruning, and quantization to the functionality. So in the same tool, you could also do some training. So in that sense, it started to solve the problem interoperability. So you have the single tool to do verification and training. That's good. But it left unresolved the other 3 problems. Then there is Coconet. It's still in development. It's a neural network format converter with graphical user interface. So you can actually graphically specify your neural networks, and then it will compile this down to neural net spec. So it resolved partially interpretability, because it's nicer graphical interface for the user. It's more friendly. But then it left unresolved the other 3. And finally, the closest to us is this Kaiser, written in a camel, because vehicle is written in Haskell, I should have told you, and Kaiser is written in a camel. So we have 2 APIs at the moment in functional programming style. And so this is a general specification language, and it does connection to several neural net verifiers. So it resolved more problems than other tools, so interpretability, integration, but left unresolved interoperability and embedding gap. This is why I'm showing this to you is not to make you very bored, but maybe because of that, but it's just to make a point that, okay, the problem was recognized, we all need to be verifying neural networks soon, routinely on our machines, as we do with SMT solvers. The problem was recognized that there is just not the tooling. You really need to be an expert in the domain to run this stuff. So people did try to lighten up the process so that we could teach our students to do it, so that any engineer in any company could do it. But it's not so easy, you know. And in particular, they're kind of structured from most naive to more sophisticated. And if you do it very naively, you don't resolve any problems really. You just have a tool that calls a few other tools, and that's all you get. So VeHICL's aim is to resolve all these problems, support the community's effort towards resolution of grand challenges. I named 5 grand challenges, and the first 2 we're not solving with VeHICL whatsoever. So we're not improving solvers, and we're not influencing the theory that finds verification properties. But we do influence the latter 3 grand challenges with VeHICL. So if we were to place where the VeHICL stands roughly in the big picture of computer science as it currently stands, we will see that machine learning methods are extremely popular in industry and in education. So you have applications of machine learning and various practical methods like regularization, data augmentation. You have some algorithms for machine learning. And then you have some theory like Bayesian methods, etc. And then, of course, this is all well established. All that's in blue is very well understood, has its own conferences, etc. And then there is this logic side of things, semantics, logic, and programming languages. So VeHICL stands in this new area, which sometimes people call neurosymbolic methods. When you get insights from both logic and machine learning theory and try to do something useful on this intersection. There is a lot of naive, pragmatic use of these neurosymbolic methods because people need them. You have a neural net, you need to verify it, so you do something about it. And what we are trying to do is, in this red square, is to get a little bit more principled approach to how neurosymbolic methods should be built generally. Luca will talk to you about the VeHICL architecture, so I think I will just suppress that until we see VeHICL. There are a few publications. None of them actually has VeHICL, the programming language, because we're still building theory behind it. Yesterday in Infer, I think we saw Peter Hearn's first paper was in 2000, and we have Infer in 2023. So we're like in 2004 Infer. So we have a few papers that just try to understand the theory behind it, and we don't yet have the tool paper, but hopefully we will one day. There are, however, instead of a tool paper, a few resources, so there will be tutorial pages for today, and user manual, etc. So we're starting to build up towards a proper VeHICL research paper that will summarize all that I'm going to tell you today in this tutorial. So the purpose for today, discuss with you challenges of neural net verification, both grand and technical, understand how logic and programming language semantics can contribute to this domain. Of course, introduce VeHICL, specification language at the user level, give you some practice. After coffee, we're going to have a practice session. So by the end of the morning session, I want each of you to verify one neural network, okay? So next time someone will ask you, how many of you verified neural network? And then there's, a forest of hands. We all verified the neural network. So people will be shocked, and your new lecturer will withdraw. Anyways, and gather your feedback as well. So your feedback will inform our future work, of course. So before coffee break, I'll introduce VeHICL. Luca will introduce neural network robustness in VeHICL. Then we'll break for the break. Then we'll have exercise session. And then I will talk to you about training side of things, because up until exercise session, it will be mainly verification. Matti will come and talk about large system integration with Agda, and Luca will complete that lot. So this is the end of the introductory slides. Are there any questions, concerns, comments? Yeah.
I had a question about epsilon form. I'm not sure if you could come back to it, but I was wondering, how do you sort of carefully choose the X out that sits in the center of the spin almost? Doesn't that sort of imply there's a perfect? What sort of optimal what we should be striving?
Yeah, so Luca will go into details, but the answer is actually very simple. You just simply take every image in your data set and take it as an ideal.
Okay.
There are problems with this because some of your images in the data set may not be ideal, but when the community does verification competitions with this, they simply take every image in the data set and put it in the center of the epsilon ball. It's a good question. Okay, so let's do it. Let's do it. So let's introduce vehicle and get practice with this. So we'll start with ACOS-GZU benchmark because it's the easiest to understand. And also, when we'll be going through the example, we will want to have discussion of programming language infrastructure that we build up. At the end of this lecture, when we formalize ACOS-GZU together, I will ask you to tell me which of the problems, of these 4 problems, we touched upon in this particular demo. So by the end of ACOS-GZU, I'll show the slide again and I'll tell me which of the properties we've touched upon. Okay? So bear with me. So this is a reminder how ACOS-GZU problem looked. Everyone is okay with this? Everyone remembers? No need to recap? Okay. We will try to verify property 3 because it's easier than property 1. At the end of this lecture, I will tell you why property 1 is too difficult for the first exercise. So let's go just at the property 3. It sounds slightly different. If the intruder is directly ahead and is moving towards the ownership, the score of clear of conflict will not be minimal. Makes sense, right? So if someone is moving towards you, please don't give the minimal clear of conflict signal because there will be a collision. So this one is about as sensible as you can get. So I will ask you, now you know where I got these numbers. What do they mean? And others, usually I don't know where I got those numbers. The engineers gave them. So this is a funny thing about neural net verification as well. There's a gap between the domain knowledge that we get and kind of as a verificationist, you just get these numbers and have to trust them. And there's no reason to think that you must trust them. But we will. Anyways, so that's our property, and we just want to implement that in vehicle. So, well, let's start to learn the language. First of all, the language has types because they exactly, remember I was telling you, this language will give some user support error messages. That's why we need types. Types will hopefully keep some kind of sanity checking of our specifications. And the very first thing you will always start your specification in vehicle would be to declare input and output vectors. Or sometimes matrices. When Luca does with you MNIST, there will be matrices rather than vectors for inputs. But anyway, input vector for ACOS-GZU, not surprisingly, is vector of rational numbers of size 5, because that was the example, and the output also has size 5. So these are really just type synonyms for vectors of rational numbers, but it's convenient to make it readable for the user to introduce the synonyms. Every specification in vehicle will have this magic line, at network. This is the name. I'm defining my neural network will be called ACOS-GZU. And it will have a type, not surprisingly, from input vector to output vector. If you look at, is it that easy? That's exactly what we want to have in vehicle. So any person from machine learning background doesn't know types, just looks at it and says, well, but that's exactly what you should have in your specification. There's what are the options? Of course, this is the right thing. Well, what else to tell you about this? So the vector type represents mathematical vectors, so a fixed length array. And maybe the interesting part of the syntax here is this at network. Thing is, we want Marabou to deal with the actual neural network as a function. We don't want to load this network or any other network directly into the functional syntax because functional languages are not very good at generally at matrix processing. So we don't, and also we don't have a verifier, so Marabou will have to look inside of that network anyway. And so we only really care about the spec and then compiling down the spec for Marabou to verify. Therefore, we use this at network. Basically, whenever you see at in vehicle syntax, it means it does some interfacing with external tools. And this means, well, this network is somewhere else. It's not in the vehicle spec. Go and fetch this in the folder. But please ensure that the type is correct. The type, it will check that your data has, your network has the right type. You sometimes need to declare values, and types for values will be automatically inferred. So for our example, because we have angles to intruder, etc., we'll sometimes need to refer to pi. And so I'm just defining pi as normal, and vehicle will infer the type. When you work with vectors, in this spec, some input and output preprocessing may be expected. And ACOS-XOO is a good example to discuss this. It is assumed that the ACOS-XOO network, neural network, inputs and outputs are normalized. That is, when you feed the data to layers of neural network, you do not directly work with units like radians and meters per second, etc. But specifications that your engineer gave you are in meters per second, are in radians. So there is this gap between what your neural network consumes and what the system engineer gave you as numbers. And no other tool that we know of actually handled this. We call this, actually the whole community, this is a consensus terminology. That's an instance of problem space / input space mismatch. Problem space is given by engineer, input space as seen by the neural network. So that's very common. And being able to reason about problem space alongside the input space is one of the first features we decided to implement in vehicle, because we believe that many errors could arise from misunderstanding of the spec that comes from this mismatch. So how do we do this? So for clarity, let's define a new type synonym. So first of all, we say unnormalized input vector is also a vector of rationals of size 5. But then we need to normalize. And the good thing is that in vehicle, we can just declare the whole normalization procedure. Before that, any of the provers that we've seen did this normalization somewhere else. Maybe some Python script would do normalization. And here we declare exactly how we normalize. So if someone is unhappy with the way we normalize, they can change it, or at least they can actually have a look. Well, minimum input values is unnormalized input vector, and the minimum value should be there. Maximum input values there. So this is, again, we could probably contact person with domain knowledge to inform us what this should be. And then you get mean scaling values. And from that, you can compute your normalized vectors. So, by the way, in the previous slide, we were concretely defining vectors. But you can imagine that for very large vectors, suppose you have, again, hundreds and thousands, that's not very convenient. So you have a little bit of support for recursive definitions of vectors. For example, this example, minimal input values. If I wanted all minimum input values to be zeros, then I could just say, and my unnormalized input vector could be of larger size than 5 generally. So I could just use the for each I construct and say for each I populate that vector with 0. Or there can be some more interesting function in there. Right, so, but let's have a look how this for each construct works in normalization function. So we say normalize. Of course, we need to annotate with a type. You will get a normalized input vector, and you need to give me input vector in return. So, okay, I'm receiving this vector. The vehicle will know that it's a vector of size 5, by the way, just by this type. And then it says, well, for each index in that vector, so this is vector indexing. Please do this. So when you fetch this element of the vector, subtract from it the value that you fetch from the vector called mean scaling values at the same position, and then divide everything by the value you fetch from this vector, and the value is taken for obviously the same position. And that's how you form a new vector that has normalized values. Is everyone okay with that? You sure? Okay. Okay, so now at least in our spec directly, we declared openly how we normalized, what were our minimum values, maximum values, what's our normalization procedure. This is already very nice. Oh, and by the way, that's our first acquaintance with functions, because before that we were only talking about types. So that's our very first proper function. And functions generally form the backbone of vehicle as a language because it's a functional DSL. So functions will use this syntax. You have a name of the function and its type. And then you give, this is a type definition, and this is the actual body of the function. It usually will have some arguments, and you define here an expression. So let's have a look at another one. So this is a function that, well, you tell me what the function does. What's the intention here? Yeah?
That's just checking if the input vector is within a range
Within the range that we've just provided, yeah, thanks. And therefore the type is bool, because here the function doesn't return me a vector, it returns a bool. Either the vector is within the bounds or it's not. And let's have a look how it does it. Well, now it says for all rather than for each. But it could, no, it actually couldn't. It couldn't use for each because we have a bool value there. So for each and for all will be reserved for Boolean values and vector values. So for all I, but the principle is very similar, right? I'm given this vector, and then I start working with the indices. For all I want that I will be to be within minimal values at that index, and between minimum and maximum values for that index. So apart from this being our second function that we ever see, that's also, of course, not just a function, but a predicate, because it has a type bool. So one of the main advantages of vehicle is that it can be used to state and prove specifications that describe the network's behavior over an infinite set of values. So I've just told you that for all, it's because we use bool, but also for all, unlike for each, can work over infinite domains. So that's the second distinction of for all from for each. And we'll have an example in a second. So let's first finish this discussion of functions with some exercise on composition of functions. Of course, if you have functions, you must be able to compose them. Otherwise, why do you even have functions? And so this is a function that's defined by composition. So norm a equals xu function composes the function a equals xu and normalize x. So could you partly infer for me the types of functions a equals xu and normalize? Yeah.
I think it was unnormalized input vector to input vector.
Very good.
And then ACAT is input vector to output vector.
To output vector. Because xu is the neural network, which I said we're not defining. We'll be referring to some file outside. Yeah. Thank you very much. So we've already used a few predefined symbols. This is to say that the vehicle has certain syntax already predefined. You don't need to define Booleans. You don't need to define multiplication, addition. And this is just a sanity check. I've just used this syntax in vehicle without explaining this, because I was assuming that as computer scientists, you will be able to interpret these symbols. They are predefined in vehicle. Let's just sanity check. So this one stands for multiplication. And this one was standing for division. And this one was standing for what? Indexing of vectors. And this was less or equal. Yeah, so I mean, this is just to prove the point. I didn't define for you the syntax fully. I was hoping that you'll grasp it because it's intuitive. And so that was one of the other principles of vehicle, is to make it as intuitive as possible so that person who is untrained in functional programming is still able to read this. Although I understand there are some people also trained in functional programming here. So that's not a pure experiment. Okay, so let's do it. Let's do it. We're very close, so please bear with me. Don't go to sleep. Don't disappear. Let's verify it. This is just a bit of, introducing a bit of more synonyms, really, because it's convenient. Instead of saying, fetch me the vector index number 2 and do this with this, it would be convenient to say, can I please reason about intruder heading or speed or intruder speed? And so we're just giving synonyms to indices of our vectors, because it will make for a nicer spec. We didn't have to. One thing to say here, though, is that vehicles type checking will keep us right. So if someone ever wanted to write, instead of distance to intruder equals 0 to distance to intruder equals 5, it will raise an error message. It will say 5 is out of bounds, because you only have indices from 0 to 4. So this is, again, one of those instances when you might want to have type system that eliminates silly errors from the code. Okay, so that's our property 3. And the first thing which we want to formalize is what it means directly ahead. And that's our function directly ahead. I'm taking a normalized vector, and, well, directly ahead is probably a property which is Boolean, right? Either it's directly ahead or not. So the type is from a normalized input vector to bool. I'm getting a vector, x, as an input. And then, well, I go and fetch the index of x that stands for distance to intruder. And I also go and fetch the index of x that stands triangle to intruder. And then I plug in these numbers. And the question for you, where these numbers come from. Is it problem space as given by engineer, or is it input space as given after normalization? First, you just might remember I was throwing away numbers for free at the start of lecture, but you may not remember the numbers. Who knows? There's something in this bit of text that should help you to understand whether it's a problem space or input space. Let's vote. Who thinks the specification is written in terms of the problem space? And who thinks it was written in terms of the input space, that is, vectors that come to neural network? And who doesn't understand the question? Or who doesn't want to risk any answer? Those who didn't respond, do you not understand the question, or you just cannot decide at the moment? I hope you do understand the question, but maybe not. Okay, problem space is what engineer gave you. Input space is what neural network sees. Well, here the hint for me is its unnormalized input vector is the one. So it's before normalization. Neural network will take normalized values, which will have completely no meaning. Remember I said engineer gave me these numbers and it didn't have meaning to me, but it had meaning for the engineer. After normalization, the neural network sees some complete gibberish that has no interpretation whatsoever. So it's important for us to be reason on non-normalized vector. Wow, this is a very simple question. You think it's very clever, but it's not. Can you spot another predefined vehicle function in this code? It's a very easy function. And yes, it's a Boolean and. Okay, well done. So first we defined directly ahead. Now it's moving towards. Well, a very quick question. So a normalized input vector, which means I'm working with which values? Problem space, as engineer gave me. Yeah, meaningful ones, or relatively meaningful ones. Okay, again, if I need to define moving towards, is again a Boolean value. Either someone is moving towards me or not. I look at this vector, and I go and fetch the index of this vector that stands for intruder heading, intruder speed, and speed and intruder speed, my speed and intruder speed. And then I plug in these numbers as given to me by the engineer who wants me to verify this. And that's all I do. And I use AND again. So that's the second. So we define directly ahead and moving towards. Everyone is okay with this bit, or are there any questions? Yeah.
Why, I mean, this is probably the engineer says, why are the speeds not relative to each other?
Yeah, sorry. It's I'm just a parser. It's a good. I mean, so I guess what it also shows to us, if you write a clean spec, right, you're in a position to say, well, I don't know, maybe I'll go to engineer and show this. An engineer can actually read it without proper training. He said, yeah, maybe it's not what I meant actually. So exactly the point. The cleaner the language, the more it will encourage this kind of discussion. And if it was as you have seen in my snapshots of other languages, by the time you understand what's written, you forgot about simple questions like that. Okay. And then finally, we just need to define what it means score for clear of conflict will not be minimal. Well, for this, we need to define a minimal score. Well, we go for index and then a normalized input vector in 5. So let's have a look. Minimal score will get an index of a vector and the vector. And then it will say, yeah, go for all the indices j that are not the same as the input that you gave. And check that norm ACOS XOO function, this normal output of normalized ACOS XOO on the vector is on that. So now let's start again. So this is actually important to understand. So remember what norm ACOS XOO was. It was, we were running ACOS XOO on normalized input. We normalize input and then we run ACOS XOO. So it will give us generally, if we just execute this norm ACOS XOO x, it will give us a vector as an output, right? Vector of size 5, because that was our output vectors. So this stuff says first execute for me the neural network, get the output vector, and then go into the index of that output vector. And this does the same, it's just for different indices. And because we are talking about minimal score, it simply says for all j that are not the same that I provided, it needs to hold that index at I is less than any other index of my output vector. And in that case, it's true Boolean value here, that's the minimal score. Yeah, so my third element of a vector is minimal if it's less than anything else in that vector. So that's what it says. Okay. Oh, that's an exercise for you. What kind of domain this for all ranges over, finite or infinite? Finite? How do you know? Yeah, and the type is? 5. Index, yeah, 5, it is a natural number. Okay, good. Okay, so to finish off our property, we just put it all together. We defined what valid input is. We defined what it means to be directly ahead, moving towards. And then finally we put not, minimal score, clear of conflict X. And that's the whole of the spec, really. Okay. All right. So this looks very easy, and this is just following the nose of the specification that we were given. A few questions just as a sanity check that we understand what's going on. Can you guess the purpose of this syntax add property? Yeah.
It's going to define it as a property to be verifying the neural network against.
Yeah, it's anytime you see add, it means I'm going to discharge it. Either I'm going to receive it from outside or I'm going to discharge it to outside. Vehicle itself is not going to verify that this holds of a neural network. Well, why not, actually? Why can't vehicle just verify this itself? Because yeah, we didn't load the neural network. So for any prover to verify this property, that prover needs to have access to all these multiplications and additions in neural network and go to do number crunching. And vehicle doesn't do number crunching. It will ask Marabou to do number crunching. So you see that property add because it says, please pass this on to Marabou. I'm not going to do number crunching myself. It will check types, but yeah, compile it to some external place. What kind of domain this for all ranges over, finite or infinite? Well, what's this for all x, valid input x? How many valid inputs can we have? Huh? Finite many or infinitely many valid inputs. What were valid inputs to start with? They were between minimum values and maximum values, and there's between 0 minus pi and something, and some numbers at the top.
It's infinite then.
Infinite is rational numbers in the interval, so it's an infinite domain. So this is the first time when we see that this for all is finally used in its full power. So it's going to be proving. Otherwise, if it was always finite domain, we wouldn't even need Marabou, wouldn't need SMT solver. We would be able to just do the testing, essentially, even if it's large testing. So this is where it's no longer testing, it's a verification over infinite domains. Okay, we've done. So the specification is over. It was very easy. Please tell me it's easy. Raise your hand if you think it's easy. Those people who answered the first question correctly were also saying it was easy. But basically, within 20 minutes, I could give you the whole spec, nothing to be done. So, well, now let's run vehicle. So you need to have Marabou installed. For this, we have packaged Marabou installation as pip install for you, so you can do it in one line. If you haven't done this, please do. You need to have actual network supplied in ONNX format. Remember, I was saying I'm not defining this. I'm providing neural network for the vehicle. It's given in the folders with exercises for the tutorial, so you're going to get your ONNX networks already prepared for you. And then you need to have vehicle installed, which is also literally just one command line, pip install vehicle lang, and that's all. If you go to the vehicle tutorial pages, you will be able to find these commands. If I have these three things in place, I'm ready to run just a single command line. So vehicle is when I call vehicle, if vehicle is installed, and verify is a mode because there may be other modes for running vehicle, but I want verification. And then there are some specifications here, so I need to say, well, please verify, and I'm giving you a specification, which is this VCL file in this folder. This verifier, please use Marabou. Network, please use this ACAS-GZU 1.7 I'm giving you in that same folder. And property is property 3. And I just click, and then very quickly, vehicle finishes, and it gives me this answer. Well, maybe someone can help me to interpret what the answer is. Does the property hold, yes or no? No. No, so the neural network is not safe. It found a counterexample. And this particular counterexample you can use and go show your boss and say, well, I found where your neural network fails to be safe. So don't use that network. Do something about it. Use different neural network or retrain this neural network, but please don't use 1.7 neural network. It's bad. All right. So the part we have just seen in the vehicle picture is this property analysis and informative error messages, and then compilation down to Marabou, and then getting answers from Marabou. So when we have 3 more blocks to cover today. Oh yeah, I promised you to ask this question. Which of these problems we have touched upon in my demo of ACAS-GZU verification? Yeah.
I mean, the big one to me is interpretability.
Interpretability, it's become easy to understand even without.
Easier than like VNN and
Yeah.
stuff.
Yeah. Okay. Thanks. Then we'll pass this on to vehicle developers. What else?
The embedding gap.
The embedding gap, because we specifically were talking. Let's declare it cleanly. How we normalize, who normalizes, what's going on, and then that led to your question and why exactly you use that. Okay. Anything else? Basically, probably that's it. Yeah, no, you're right. And I promised you to talk about why I didn't do property 1. It's all about embedding gap. We have, remember, half of you were sleeping when I was talking about normalization, minimum values, maximum values, so thinking, I can't bear this any longer. Well, for property 1, I would need to do the same for the output as well. In some cases, outputs are scaled, and you need to also normalize outputs, so that's why I omitted this. So definition of property 1 in English doesn't look much worse than the property 3. But the devil is in these details. The ACAS-GZU network outputs are scaled, and there's some formula to scale them. And so when you put your specification in, you'll need to declare the scaling and define this. The score of COC is at most 1,500, actually in scaled numbers, not in 1,500. So there would be a little bit of more tedious work to do this. So that's why I didn't introduce it. But it's a very simple exercise. If some of you are interested, there are answers, ready answers for this, or you can work out your own. But this is just to say it's useful to have a tool where you could transparently work with the embedding gap and get these old bugs out. Because it took us a while to realize that this is happening, actually. It wasn't declared anywhere. It took us 2 years to understand that scaling is happening. But now no one has to do it again. And that's...
How did you figure out what the 7.5188?
Oh, you dig into one file and the other file in different VNN competitions, and the file refers you to Python script that does some normalization. And in some Python script deep down, you find that someone scaled this like this.
Right.
Well, I guess, again, when they were writing paper in 2017, maybe the engineer told them, by the way, this is what we do on these aircrafts, on those neural networks. But the knowledge gets lost and then forgotten or whatever. Okay, any other questions? Because Luca will go and do the hard stuff with robustness, epsilon bolt robustness. Okay. Yes. Sorry. Yeah. You can have 25 minutes.
Oh, you cut me short. All right, so I'll try to keep this in 25 minutes. Luckily, you've covered a lot of the things. So, right. As Katja mentioned, I'm now going to go dig a little bit deeper onto robustness, if I figure out this pointer. So Katja already mentioned this, so I'm not going to go spend a lot of time on this. But actually, the paper she referenced in 2013 was this one, which is an image much more complicated than the 28 by 28 grayscale index images. But effectively, what they showed that this neural network with classified panda with a 57% confidence, all of a sudden, with a completely transparent noise vector that was put to it, was classified as a gibbon with then 99% accuracy. Now, this is particularly scary because I don't know about you, but if you look at that gibbon, it's exactly identical to me. So as Katja showed you an example with the Akasu, she was dealing with numbers, etc. Now we're dealing with images, and we don't really have very nice definitions of what is a panda. We don't have a nice impact vector saying, this is the distance to an intruder, this is the angle you're taking, etc. We need to be able to say a panda will remain a panda without any definition of what a panda is or what a panda is mathematically. So the approach we take with some neural network properties, if we want to say that if two of these images are close enough to each other, they will be classified within the same distance. Now, this is a very generic way of saying that if you have a neural network, you have an input of the training set. So somebody was asking about how do we choose the images. Well, we take it for granted. That's a panda. We know it. It's labeled as such. And if we have some notion of distance, which there are several, but let's just say as long as it's only shifted a tiny little bit or a small amount less than epsilon, then the classification will only shift by that little amount. Everyone happy with that? Do you understand why we're doing this? This is kind of important. We cannot say this is a panda, so we got to be able to say, in order to stop that attack, in order for this noise right here to not change it to gibbon, we have to say as long as the image doesn't change too much, it still says a panda. Or it still, the shift of prediction changes much. Now, Katja, I think already mentioned this. I think, yeah?
Just for previous is that epsilon already has
The epsilon is over the, in this case, problem space of the actual images. So it's a change between the values of RGB values.
And these are not both epsilon, right?
Yes, correct. This is a mistake. So this is a famous data set. I think the 5 people who raised their hands saying I've done machine learning in class probably trained it on this. This is the NIST data set. It was created by LeCun. And it's a bunch of handwritten digits of numbers. They are actually represented as 28 by 28 tensors. And they're often used as benchmarking tasks for machine learning models. So you train this and go have 99% accuracy to recognize a digit. Now, these are often used for representation tasks. And I want to note these are slightly different from what we saw with the spec with VeCo, because we actually need to represent these images within the language. But the same exact problem holds. This is what Katja already showed you, so I won't spend much. Still, even on a tiny little vector, which is 28 by 28, really tiny, still causes issues of invisibility, so you can't see any different there, and causes large significant changes. And that's simply because it is the new image is no longer in the probability distribution that this network has learned is 0. That's just simple as that. But you can see that even on this simple example, these are quite effective. Now, let's look at this property that I defined earlier in a little bit more detail. So this is like a high-level thing. So if we have a neural network, which is a function for input to outputs, there is a property on the input x and an output property, which is qy. If you were at your talks yesterday using p and q, you should be quite familiar with this syntax. More or less the same, except the thing in between is a massive neural network. We don't know how it works. And you want to ensure that if the property is satisfied on the input, the corresponding output is satisfied on Q. So we know that this is an SMT solver, so we always phrase this as we do not wish for. That is just how you write these queries, SMT solvers. If it is satisfied, a counterexample is returned. So if we find an instance where this does not hold, and we saw that example exactly in Katja's slide, we saw some set of inputs that caused the property to break. Now, the most common property, the one we'll be looking at this, is robustness. This is one variation of robustness. There are several others. That is a bit of needle haystack, which I don't want to lift too much here. Let us just say that given two images which are similar enough, or rather the epsilon only changes by a little bit, the classification doesn't change, right? So we have a panda, we shift the inputs a little bit, we want to maintain that it's still a panda at the end. This is called classification robustness, the simplest one to define. And in fact, we're saying that the set of outputs, the numeric values of the ordering of what it expects it to be. So when you have a neural network, it outputs, I believe it's a panda with 99% confidence, a cat with 7% confidence, et cetera, you want that ordering to stay the same. That's why we're ordering it right here. Okay, so then if we go to epsilon ball robustness, we have an infinity norm. So I told you there are different distances. We're effectively saying a distance within an infinity of the value within a new value will still be less than epsilon. Like I said, there is quite a few of these. Katya will mention them in her part on training. And if you guys want to go feeling particularly excited about this language, you get a chance to do it in the exercise session and try formalize a few other of these properties. I'll mention them at the end. Everyone happy with the formalization, what I'm saying? Hopefully it's nothing too new. I'm just kind of rehashing what Katya said, because now I'm about to go write it in VeCol, so you need to be able to understand what I'm doing. Everyone happy? Perfect. Again, this is a final pictorial representation. We're saying we're creating a range of images whereby within this distance there are always 7, and simply this is what it looks like. Okay, so I rushed through this because I wanted to get to the language. Anybody has questions as I write along, please let me know. I should be able to do this. After USB-C, does that work? And you want me to record here? Yeah. All right. So, can everybody see my screen now? I pressed the button start recording. Yeah. Yes, I'm just recording my screen for everybody. Can everybody? I think this is a bit too small. How do I make it bigger? Is this better? Can everybody read this?
Yes.
Oh wait, what am I doing? This is way too early for this. Can I switch back to the projector? I wanted to introduce some syntax before going to this. I guess I could have done it. Yeah. Apologies, I forgot. Right, sorry, I forgot before I got too excited about programming this and actually forgot that I need to introduce to you how I'm going to do it. So apologies for that. So the main differences between what I'm going to do and what Katya did earlier is this example is a bit more complicated, meaning it has images. So we actually need to formalize images as in VeCol, and these are going to be 2D arrays, as Katya mentioned. We need to define some parameters according to the user. So this epsilon value is for what can be given by engineer and hard-coded, just like the Akazu properties, but perhaps you have a very specific epsilon value you want to use yourself, and VeCol allows you, for sure, to actually write that yourself. So to go over all the types, I'm going to go over them quickly, just because you're aware of them. I'm not going to spend too much time on it, but this is a type language. We have Booleans with all the expected Boolean operations. Indices, this is just a list between 0 and n. You already saw them in the Akazu example. Natural numbers, int, and rationals. As Katya mentioned, mostly we'll be dealing with rational numbers, but for the sake of VeCol, we're happy to use them. Then we have lists with fold operations and mapping. Then the most important one that we'll be using for verification is tensors, which are dimensions and typed. And this is used for important when you know the size of. So the size of images is fixed. You need to know this. The inputs of the neural network, the outputs of the neural network, these are all fixed. Worth noting, VeCol can infer these automatically. So when you load an image dataset, and I'll show you an example of this in a second, I can infer the size of the image automatically, which is quite handy. If you don't know it, 28 by 28, it takes away a lot of work from the programmer. Then we can do normal operations. That's how you write operation. Katya already asked a lot of questions. How many of you know functional programming? Okay, that's good. Okay, so quite a significant part of the audience. That's good, so I don't have to go into details. Everyone's happy with the bang that are very hard to remove. Anyway, so a network. Do I have a laser pointer? No. The network data set is is the important one. Katya already mentioned it. I'm going to mention it again. This is where you're loading a network into VeCol. And like Katya said, you're not actually loading it. You're just saying this is the etc. and you're giving it to that thing. It has dimensions and an output. A new one that I've mentioned already that we'll be using now is a data set. These are the images we'll be using, and they are represented in vehicles. You can actually say, when I said a little shift within the images, or two images that are similar enough, this is actually what we're looking at. Nope. And then we have parameters. This is the one, and the new keyword as well. This is passed from the command line when you actually call the verification, so you can have parameters. And you can actually infer parameters automatically as well, which is an extra feature that it has. Like Katya already explained, type synonyms, conditions for all, quantifiers. So I won't show much details, but we have this. We have the syntax here. Okay, so this is the case study. I have it on the slides, but I'm actually hoping to do it from the laptop. So now I'll be switching. Sorry, I anticipated that earlier already. How's that work? HDMI, I want it. Okay, so should be back. All right, so this is going to be interactive, so I want you to shout at me. We're going to write out the whole NIST spec, which is the robustness neural network, together as we go along. Now, this you will get a chance to do on your own later in the exercise session, but I thought it'd be a good starter so you get an idea of how to do it. For the people who are not comfortable, people who didn't raise their hands when they say functional programming, I thought it'd be easy. So the first step here is to define the type of our input images. Now, I already told you we're using a NIST data set. Who remembers what size they were? Perfect. And how would we define a 28 by 28 image in VeCo? Tensor of type
28.
rationals 28 by 28. So this is as easy as that. This is our image data set. This is the size. Now we want to type the output labels. How many digits are there? Well done. 9, but okay. So we're doing the digits now. So we want to do a type label. This is what the neural network is labeling outwards. And the way we do that is we do an index of 10, which is from 0 to 9. Because we're sane and we're not like the MATLAB people. Then we want to say what is a valid image. So a valid image is, so once again, we have, in images we have a state where we want it's normalized, so we want every single pixel to be between 0 and 1. Okay, so we want to say that, again, in infinity space, when the values we range over, when we do the verification property, to always be valid. So now we can write a function, we can call it valid image, and typing in front of people is scary, but I'm sure I can correct me if I'm wrong. And it takes in an image, and we're saying it's a valid image, so what's the expected output? Very good. Perfect. And then we want to say that valid image takes in an input x, and what does it do? You want to check that for all inputs. What does it do? Shout out to me, I don't care, I'm not going to call your hand. So we just said that if you could...
You're just checking if both I and j are within the given range 0 to 1.
Exactly. And the way we do that is, so the lower value is 0, so 0 is less than equals x at I at j, no? And then it's less than and equals to 1. Okay, so then we have to declare the network. Here, this is very simple. We just call it classifier or whatever you want to call it. It's worth noting that when you state it here, so you will see here I've done some verification at the bottom. When you actually call it, you need to use the right names. So here I call it classifier. So whatever you call it here, this name sticks. And what is it classifying as inputs? Images. So we're taking images and turning them into labels, exactly. Or yes, you can even do vectors at 10. I've done types, it's nice, but you don't have to do that. Okay, so now that we have the network, we have a parameter. So this is the epsilon value. This is the little amount of change you want to avoid when you get it. Now, we could write it down here, but actually all we want to do is type it, so we know that the input to the user is correct. Rat. So what we're saying here is whatever is passed when we call VECO has to be of type rational. After that, I don't care. You can send me whatever you want. So this is quite nice. It actually types check this, that you call it correctly, but allows the user to then do whatever their things. Okay, I missed something. So we want to be able to advise that what they're actually doing. So, I'm not reading the comments to you. Do you want me to? Everybody's happy to read. So this is effectively what the classifier is doing. So the classifier is taking an image. It's taking a label. And it's making sure that that for the label, I is greater than the score of any other label. So this is the property I was showing you earlier with the y's at indexing less than equals to the xy. So this is what's saying that Gibbon will always be the highest ranked label. Everyone happy with that? So we're then taking image to a label, and then we have a Boolean. And then we go advises, xy, xi equals. Then we're saying for all that j, this is very similar to the one catch I just showed you earlier, so I don't really need to show it too much, but we're saying that whenever j is not equals to I, the classifier x at I is greater than the classifier x at j. Everyone happy? So this saying it classifies the input, it always stays the highest input as the one before. This is the property I showed you in the slide, yeah? So we're saying that the so if you get an image and it's labeled as a Gibbon, the output of the network will say the Gibbon is the highest possible scoring system that it gives. So remember, the output of a network is, I believe it's a Gibbon with 90% accuracy. I believe it's a monkey of generic type with 6% accuracy. I believe it's a panda with whatever accuracy. No matter what happens, you want to say it always maintains that ranking. Okay? What it means is this is classification robust. So we haven't written the rest of it. So we haven't seen the robustness thing. We're just saying that at the end, no matter what inputs you change, you will still have the same advice. Okay? So that's where we're adding it here. We then already have the parameter. Then we want to be able to say what it means for the image to be bounded. So we want to say that an input is within it's within epsilon, negative epsilon, and positive epsilon. So the change to that point is only epsilon. Oof. Bounded by epsilon.
If take 5 or 10 extra minutes, that's okay. Just go into the boundary.
Okay, don't have to rush. Anyway, so we take in an image, and we convert a bool. So this is a bool because it's just a condition we check. We check to make sure that the change is not too much. Then we then go bounded by epsilon for x equals for all I and j less than epsilon. Epsilon is the value that's coming in from the user. So this will type check. Even if you run it without thing, it just checks that the epsilon is actually rational. And it's less than equals to x at I, j, and less than equals to epsilon. Okay. What should we grab here? Ah, yes. Thank you for spotting that. So yeah, it was a test and nobody noticed. Okay, so now we actually get to write what it means to be robust around an image. So this is the actual property. We've written all these things. We have done all these nice functions to put there. Worth noting, I didn't need all these auxiliary functions. Could have done it in a really messy formula, but this is one of the advantages of doing this, so might as well. So to be robust around, we want to take an image, an output label, and a Boolean. So we're saying that given an input and an output, we are robust, okay? Everyone happy with this? Okay, so this is I'm going to ask you a few questions now, so you need to have been listening. What's the input of this? An image and a label. What do we want to say now? We want to say that for all different changes, it will always still advise the same output, right? So we want to say for all perturbations, and you can note that even though my spelling is terrible, you can use some quite nice, almost English written syntax. We want to say for all perturbations, then let the perturbed image equals the original input we're putting in, minus perturbation in. And now this is where the function by in. We want to say this is within the epsilon value, so we can say bounded by epsilon. Perturbation and valid image, which I've put at the top right there, is any image that is within the range of 0 to 1. Valid image, perturbed image implies that we're going to advise perturbed image enable. Okay, so I've read it all out. Let's actually digest it slowly. We're saying that if we take an image and we perturb it, and the perturbation is within the epsilon value we have defined, and the output is a valid image that's between 0 and 1, then we will always classify this as the original highest level ranking that image was given. So in few words, if you give it a gibbon, you mess with the pixels by only as little as epsilon, you will still classify it as the original label. So now hopefully you see why I did all the functions. Now this is where we actually get to play with it. Yes, you're right.
Pick up instead of the top.
Background image label equals
Line 48.
Line 48, robust around image, image label, full perturbation.
equals instead of dot. Not here, yeah.
Yeah. Delete that one. And then
Oh, yeah, sorry.
label equals.
Sorry, for all perturbations.
After label, image, instead of dot. Image.
Yeah. Sorry. Yep. Happy?
Does the in have to be lowercase?
Ah, yes.
This advisors spelled wrong.
Yes? It's very hard to type this in front of people. I thought this would be very easy. Okay, so what we're doing here. We're doing now, this is the, yeah,
Sorry,
another one.
I might miss this, but what does for all, so like in all of these examples, not introduced, like we're introducing the variables that
Yeah.
for all ranges over immediately afterwards.
Mm-hmm.
And obviously in the like bounded by epsilon example, it seems quite reasonable that vehicle can infer what I and J range over.
Mm-hmm.
Especially because your they appear, you know, on the right hand side of
Yeah.
that dot. But in this robust round function, you've done for all perturbations. Is that a function? Or is that
This is, so as Katja said at the very end of her talk, this is infinite. This is any perturbation within the range of 0 and 1 will be checked. So this is verification. So it's saying any perturbation that matches this spec, so it's valid, bounded by epsilon, etc., will be checked. So it's iterating over infinite values.
so? Yes, I'm just wondering how it infers shape of perturbations as well as being 28 by 28.
The perturbation will be a value between 0 and 1. Sorry, within minus epsilon and positive epsilon. They then gets applied to the particular value within 0 and 1, right?
Yes, sorry, that's per pixel?
Yes.
Right, so it is when you do, you know, let perturb image equals image minus perturbation,
Yeah.
like does vehicle kind of infer the shape of the perturbation thing as a 28 by 28 grid of
Yeah.
perturbations, or are they all the same perturbation? Like, are they all the same?
I think because perturbation here is an argument to bounded by
Yeah.
epsilon, and it has its own type.
Right, it's from the type of bounded.
Yeah.
Okay.
So it's, taking image booleans. Sorry about that, yeah. No, that's great questions. Thank you for bringing it up. So, now, we're actually taking data sets. So we've written that the neural network is taking 28 by 28, so we're cheating. But we actually can infer this value from the image we're loading. And I'm almost done. I'm realizing I'm running a bit over. So we're doing this parameters, which is just going to be the size of the network. It's going to be of type NAT. And this, you can see the keyword infer true. I'm not even going to pass it to it as an argument when I call it. As you can see here, I never pass it. I just pass it a data set, and it's happy with that. It takes it and automatically does the size, which is quite advantageous. Then we take the training images, which are just a vector of image. And it's taking n from here. We do the same with the training labels. And then we write the overall property.
So
Now,
these lines exactly your question, where do we take ideal
Yeah.
images? So these three things that you could just show when you get n and then data into data label is exactly based on these the ideal images from these three. Yes.
and now conscious that I'm kind of almost over the time and I want to show a couple of slides just to preset the next thing, I'm going to let you do the property when you come back from the break. So I've written all the spec out. It should be really easy from here to just say what it means to be robust around. I've given you everything. You've loaded the data set at one point. You should apply the function to the image and training classification set. So hopefully now you have a pretty good idea of... Does this work? Yep. So hopefully now you can see that we have this condition in math and we have all the things training set, and I actually did in the slides. Hopefully now you can do it yourself. To run the vehicle, all you need to provide is a specification file, which is what we just wrote. The network in ONGS format, this is a standard neural network format. The data in IDX format, that's the original format that the images came in, and it's a standard way of doing it. And then the desired epsilon value. You call it like this, and you can run that spec that I just gave you to verify this. And it's worth noting, since there are internet values, what Katja showed you as a very complicated VNN formula, this is something like 800 files to actually verify this in Marabou. And this is what vehicle actually generates for you. So concluding this exercise, which things have we showed in this chapter of these PL problems? Shout them out.
Interpretability again.
Yeah. What else were we able to write nicely without having to deal with low-level stuff? Correct. So all the types were able to address the embedding gap. We never had to deal with these crazy formulas. We just were able to say for all images and move from there. I guess interpretability. I hope that code was quite easy to understand for everyone, and hopefully it will be very easy after the break. So we are pretty much done for this session. Before the exercise section, please run these two commands on your computer so you can actually install Marabou and install Vehicle. And then if you go to the website link that I should have given, there we go, you can actually be running these exercises. So there will be a couple of exercises. I'll be giving you some code with a variety of data sets. You get to try this out yourself, try out different epsilon values, etc. And there's also a couple of more difficult exercises with different types of robustness.
Okay, so yeah, everyone, we're starting the exercise session. The deal is we ring-fenced about 40 minutes to do exercises because, because it's more fun to do exercises, and you'll remember this better and understand this better if you try. The gentleman you see here is Dr. Matthew Daggitt, who introduced the start as one of the main developers. So he will be he's in Japan at the moment and in the process of moving to Australia. He will be with you on the Slack channel, and I'll show you in a second how to join the Slack channel for Vehicle. He will also give us a little demo of Agda integration because Matthew is a developer of Agda standard library. Agda is his favorite language, as I understand, so he's the best person to explain how Vehicle is integrated into Agda. So he'll give a little lecture as well. But for the exercise session's sake, I think so. Please meet Matthew. Matthew sees, no, he only sees me. But please, if you are too shy or if you have questions later, please use that Slack to which we'll link you in a second. Okay, and now can someone switch me back to show the HTML, this screen? Thanks, Matthew, and I'll see you later. Yeah, so this is the deal. If you go to the VeTSS main page, it says for this tutorial, please look prerequisites. So if you click on that link, you will land on this page that talks about prerequisites. But in fact, this is just the whole of the Vehicle tutorial, and that's a prerequisite section. So if you go in particular to this introduction, to the very start of it, you will notice here we put a link to the Slack channel. So this Slack channel will be permanent. If you start using Vehicle and you want to engage, or maybe you want to be our collaborator, come to us as a student, postdoc, I don't know, or just collaborate without any contract. You please use the Slack channel to reach to us, as well as our emails. But for now, if you wanted to communicate with Matthew or other developers who will be there on Slack, please subscribe to the Slack channel. But yeah, we're going back now to the prerequisites page, because this one is really the most important one. Is is the Slack channel here. No, it's okay. So I'll go to prerequisites. The installation was made specifically so easy for the tutorials, so we really encourage you in theory, and this hasn't been already tested at CAF, you only need to run these 2 installation lines in Honest, so nothing else. Doesn't work?
You need Python 3. It does. Use Python 3.10 and do Python 3-m pip installing, and it doesn't. We just tested it there.
Okay, so Luca will come to you. Just raise your hand. Luca will come and help you to install, but with the right version of Python, because pip is coming from Python's libraries. It should install nicely. So if you're very, very lost and you don't really know what's best to do, the best thing to do is to go to this tutorial repository that's linked there. So the tutorial repository is made very, very simple. There are only examples and exercises. Examples is what we were using to run the lecture slides. So if you just want to make sure that our lecture slide code runs on your machine, you just go to examples and run the command line. Usually, in fact, if you go there and say you're getting started equals XU, you even see in the README file the command line that you need to run, right? So there's like a full support for you. But what we refer you to better than just running our examples is to go to the exercise folder. And then again, chapter 2 is for equals XU, in this case IRIS, but we like you to go to this chapter 3 and run the exercises there. Okay, so are we clear where you get the code? Because this is all well, let me show the example. For example, this MNIST complete specification. Why we organize this in folders? Because to run the verification query, you need to have a few things there. You need to have ONNX format for the network, you need to have data, you need to have a specification file. That's why we just put this all to you all in one folder. If you get the whole of the repository on your machine, you'll be able to just run everything from that folder. Okay, and the exercises we're suggesting for today, I will show you in a second, but let me just see that everyone's happy with where you get the code. So 2 installation commands to install Marabou and Vehicle, and then once you do it, you just get this repository to get all the necessary code to run the queries. Okay, let me go back to our landing page. That's quite a while ago. Okay, so the exercises we're proposing will be devoted to chapter 3. So these prerequisites is simply giving you the installation commands and this tutorial repository there at the bottom. But the exercises are at the end of chapter 3, so that's why I actually scrolled to chapter 4, so that's just to get quicker access to section 3. Every chapter has its own exercises, and we don't expect you to do all. Some of them require a day to run. But we recommend 3.1 is simply run this chapter code. This is just to test that you installed everything. And then to get yourself familiarized with the code exercise, with experimenting with different sizes of epsilon ball, what happens, so 352. We recommend 353 is too long for you to run now, but you can do it at home if you're interested. And then 354, implement a different kind of robustness using the same Vehicle file that Luca was using, just change a few lines and see how it runs. And I'll probably stop here. There are more exercises if you want, but I suggest we just do 3.1, 5.1, 5.2, and 5.4 as a warm-up.
If you're very keen and you want to call us over and you think you're doing advanced ones, feel free.
Yeah, no, we'll suggest you more exercise if you're done. But this will, I think just coming up to the end of 3.5.4 will give you a feeling that you actually got your hands dirty into the code and you can hack the existing specifications. Anything else I forgot? No.
Any questions before starting?
Well, you can ask questions anytime anyway. So, okay.
I gave you a task to write the property. Now, the smart of you will have found that answer very quickly if they've been downloading the code and actually running it. Does anybody want to volunteer this property to me now, or do you guys want to do it together? It's okay if you're reading from the examples. I'm completely fine. Just want to make sure you download it and are happy. Yes?
I know it starts with some sort of for each.
Yes. So, yeah. Anybody else want to try give it the whole thing, or should I start writing it out? Okay. So the first is robustness. So we want to say it is robust against a vector of bool n. So this is the set of properties, and to be robust, is it recording the audio?
I was going to say you're recording on a laptop.
Oh, I'm not. Apologies. Okay, now it's recording on my laptop. And to be robust, you want to say for all or for each?
I think it's for each.
Yes? Well done reading. And you want to say for each I, which is for each image, what? Well done, my lad. What is robust around? No. Okay, so this is the function we wrote earlier. This is the function that we made sure that within a distance of perturbation, it always advises the same output. And we want to say for each training image, I, we take the output, which is the training labels. Now, it's worth noting, these here, I'm using them as variables here, but these have not been loaded in yet. They're loaded dynamically when I call the verifier here. So if you see here, training images and training labels are actually being loaded there. Now, I have no idea where I put my own incomplete VCL spec, so I'm going to run this one just to make sure. So let's go a little bit over the thing. Vehicle is the program I installed by doing pip install vehicle lang. So now I'm able to call it. The first parameter is the specification, which is this file we've just written. It's called NIST robustness.vcl. If anybody of you open the examples folder, you should have this exact file. The network, we're calling it classifier because remember, in the code itself, we give it the name classifier. And we're saying the classifier is the NIST classifier.onNX. The parameter is the epsilon value. So here I'm using 0.005, which is a very small epsilon. We're saying a very small perturbation. I encourage you to play around with these epsilons and see what it looks like. Worth noting, the larger that value, the more the disruption to the image. So at one point, it's no longer a stealthy attack that hides pixels here and there. It's your image doesn't look like your image anymore. Of course, you're classifying it wrong. So normally 0.05 is the value that's verified. Training images teach you the image of IDX. Training labels teach you the labels. And the verifier is Marabin. No? Yeah. So it's running this property, so you can see there are 9 queries, even though we only had 1 property. Due to the for each, it's actually creating these queries. It's running through and checking if it's robust. It's going to take a second. You can follow along from your computers if you want.
Well, here the interesting bit is it's going to only look into 2 images. So remember, it verifies epsilon balls, and you see robust 0 is the first image in the data set, and this is another one, and that will be it. This is because the data set that we provided only has 2, and we did it so that it's quick.
Yeah.
But it infers how many images you passed over the exercise session. I had a question how it's not testing, because this looks like testing. We go into a finite number of images, but around every of those images, we verify the infinite input in the epsilon balls. So that's how it gives you the power of full verification. That's why you need to call Marabin.
And by the way, if you go to the examples format, there is a different data set with all the images. If you have 10 hours to spare, you can run it. And so you can see this is robust. So we can tell this network for these properties is
around only those 2 images.
correct. Anybody had a play around with these epsilon values? What happens if I raise the epsilon, make it bigger? How does it?
How quickly?
I just went straight to 0.5.
So what we're saying here is this is a huge value. The range is from 0 and 1. So you're effectively changing it completely. So if it's at 0, it's going to 0.5. If you imagine an image, this does no longer look in any way like the original image. So it's almost useless to verify this. Worth noting,
Epsilon 0.5 is actually verifying.
oh, sorry, the other way around.
Because it's
Yeah.
distances and they start multiplying.
You're correct, the other way around. Sorry about that. Worth noting, finding the right epsilon is tricky. So like we use these as benchmarking. We don't really know what the best epsilon is. There's no official guidelines on what epsilon you should use or what makes sense. Ideally, you want to find the optimum epsilon that visually is still hidden, but may cause the change in classification, and use this epsilon to verify. But that, unfortunately, is not hard to find out. This will take a lot longer, so in the meantime, anybody who hasn't got a chance to run it yet, you get to beat me to it. In a few minutes, we'll be showing some other examples. Anybody have any questions about this one in the meantime? Anybody having trouble running this? There's a question up there?
Yeah, I think you might be about to mention this actually, but you used
Yes.
Is that, I'm not a machine learning person, is that normal? Like is that the normal distance metric that's used in image classification?
There will be, yeah, some papers in machine learning are surprisingly okay with it. Obviously, you would think Euclidean distance is the most natural, especially if you talk about epsilon ball. So if you use infinity norm, it's epsilon cube really, because you
Because it's only the one.
yeah, it's not a ball per se. But in many machine learning, it's just so much easier to compute. It's faster, so in many machine, like same with ReLU activation functions in machine learning. You'd think, well, surely you don't want such a simple activation function, but for the sake of performance, very often people are all right.
And it does the job well enough.
Yeah, it does, usually does the job well. But certainly for verification purposes, if you change the distance, Marabou will not take Euclidean distance because it's no longer linear. Yeah.
I realized this took this long to run.
You can use vehicle also for training, and therefore you can have some queries that Marabou would not take, but you can use them for training. That's why the specification language of vehicle is richer than what Marabou can have.
Oh, yeah. All right, this is going to take a while to run, so I'm going to give it back to you. Have a test with this far, and then, oh, you have a question.
Yeah, sorry, I'm not machine learning.
Yeah.
So it might just be my naivety, but surely because we can choose the epsilon, we sort of set bounds for us. So I don't understand why we should be allowed to choose the epsilon value.
Yeah. So you can always hammer it down to success.
Yeah,
because
change
No, this is absolutely true. But the game is, right? Think about now you're using this in an autonomous vehicle that tries to use a stop sign. Of course, you can make epsilon arbitrary small, but then in real life, no stop signs will fall within that epsilon. Because if you do sell this as a verified neural network to someone, what do you sell? You say, your neural network is safe for this epsilon. So your autonomous car will always be trying to see whether the new image it sees is within epsilon value of any of the images that you verified already. And if the epsilon is tiny, no real life image will simply fall under your verification bounds. And so you're as good as having no verification, except for your car also spends time actually checking whether the new image falls within epsilon balls. So the game is, if you were serious about this, if you were to sell it to industrial partners, you would say, I increased the epsilon, so now you actually can catch some bad cases. So there is a trade-off. In theory, you can always hammer this down to success by getting small epsilon, which is impractical for anyone who's interested in real applications.
I also have a slight minor follow-up that's in a different direction, but this all sort of reminds me a lot of both real analysis, which I suppose is like the sort of epsilon delta, but also coding theory. In fact, the spear packing bounds. Is this something that is used or is analogous in any capacity? Because it's sort of, we have these radiuses where we go outside.
various interval bounds propagations and abstract interpretation techniques were thrown at this problem, particularly with epsilon ball, because exactly you're working with bounds, and then you can reason about the bounds. So yeah. If your property of interest, specifically epsilon ball robustness, that's how many verifiers multiply it, because there are many other computer science areas that look into bound propagation. So no, that's absolutely good intuition.
But I've talked to a lot of safety people who don't do security, but they often operate under the safe domains of operations, and exactly what you're talking about. Like, as long as it's within this range, I don't care, or I can get the guarantee for this range. That's all you can do. That's good enough for most scenarios, hopefully.
Okay, Luca, what did you do? You made very tiny epsilon. And what about
the other one just crashed.
All right.
I think my laptop is out of RAM.
Okay.
But yes, I do encourage you to test this on your computers. You can see different results, and you'll see eventually this property fails if you do this number changing a while.
Let's see if anyone tried. If no one attempted the strong classification robustness, then maybe we'll just go forwards. Only if someone tried, has someone? Could you show the HTML page, Luca, for a second? We'll just, so that people know what I mean. So Luca has just covered the answer to 351, 352. And the next one we asked you to look into is the 354, basically substituting the robustness definition we gave you with a different definition. Has anyone tried to run this? Do you want to? Okay, let us give you 7 minutes, right? So this is the task. You take the complete MNIST robustness file as it's running, so hopefully if it's running on your machine, and go and find a few lines that you need to substitute in order to substitute understanding of robustness in that file to this new understanding of robustness.
Remember, the previous property was, when you make a classification, always make sure that no matter the change, it will be within the same class. And that was the ordering I showed you. You have to change that now to fit this mathematical property.
You're saying, I say my network classifies this as a label I if the I's output of the network is greater than it I give you.
Even if you get to the point of which lines to modify, but you don't not sure how, that's already very good. And then we'll show you how.
Yeah, look, I pushed the file.
You push the file. You need to git clone live and see everything break.
I guess we showed just the simplest solution that assumes that the outputs are scaled and not bother with the longer one. It's probably better to cover the theoretical stuff now.
So it is the tutorial between exercises?
Exercises proving robustness, then complete MNIST, and then there's SCR, somewhere this MNIST SCR, strong classification robustness. So if you hide part of the code that does, if you go down, so we'll just give a simpler version for the sake. So if you stop right there.
No, it's right here the problem, so we want to avoid that line.
You want to avoid that line, but it's not used. So if you go down, hide this and just show eta. Show at the top of the screen eta. Don't worry, or remove it if you like. But it's just this and this line, that's all we need.
Yeah, but I'm doing it once.
Usually showing an answer. It shows which one gives an error and which doesn't. Yeah.
Okay, so according to the schedule, we're doing this or?
So I'll try to finish in 30 minutes and then I'll give it to you in Matthew. Is that okay?
So we'll finish in 20 minutes and then we're 50 minutes. Yeah, so I can do it in 10 and then less.
Okay.
Okay, so as long as you finish by 12:05, latest 5. So we finish this, I pretty much we're done. We'll go back to the session.
Okay, so maybe actually for the sake of time.
There, do you want to wear it?
Yeah, okay, for the sake of time, we'll probably.
Just wait, sure, I'm sure.
Okay, great. So maybe we'll give you a very quick answer now. There are plenty of other exercises you could try. So if I wanted to change to a new definition of robustness, and there are several, So I just need to define eta. Remember my specification was saying, well, I need to have an output of on certain index less than an eta. So I just say, well, parameter is going to be given, and I advises that function is going to be changed. So for x and I, it will give a true if the classifier, I apply classifier to the input, I get the output, and then I get the is index, and that index is greater than eta. And because this eta is given as a parameter, I'm going to call it as other parameters as epsilon through the command line. So this obviously assumes, usually eta is 0.5, and this assumes that my output is scaled as well. So there is a little bit of an exercise here. What happens if I try to scale them in the vehicle, and there are some troubles with Marabou, but I will not, if you're interested how to make the good spec and bad spec out of it and why certain things fail, find me at the lunchtime and we'll discuss more of it. Can we switch to, so this is the end of the exercise session. I know it's, there is a threshold for you to just install everything and run, but actually once you, no, I need slides if that's okay. Once you get this installed, playing with the specifications is not that hard, so I do encourage you to try. Later is fine, so just use the same Slack channel. Okie doke, so we'll go into the chapter about training. And we will discuss why and how training is part of verification of neural networks, what choices exist for implementing this generally, and what choices vehicle makes in this respect, theoretical and practical issues with the chosen methods and vehicles' take on them. So in terms of our 4 problems, this now touches upon the very first one, which we haven't yet discussed, interoperability. We discussed that the trouble was, in all the previous approaches, that people would train it in Python, then verify in Marabou, and there was a huge gap. Sometimes the property between it travels from your understanding of what happens in Python to your understanding in VNN lib standards changed dramatically. And there are other problems, as we will see today, with that. So why training is needed at all in verification? Because in your standard verification efforts, you don't retrain anything. Well, because of these examples, right? This is from this morning. I wanted to verify that property 3 holds, but this is a counterexample. And so my boss tells me, well, find a neural network that is verifiable. What do you mean it's not verifiable? Should we hold all airplanes in the country or what? So give me a good neural network. So I need to go back, take this neural network and retrain it so that next time I run this command line, it says no counterexamples found. This is one of the exercises that you're asked to do on the exercise page if you have a day to do it. So if I was to choose 500 samples, and I'm using slightly different data set, fashion amnist, and then I was trying to play with different epsilons, you could see that as I increase epsilons, I very quickly hit. So for example, for 0.1, only 3.8% of my images are verified. It really means that, you know, I'm giving very little verification guarantee here, but on the other hand, I'm giving a lot of guarantees here, but epsilon is so small that no new image will fall under that. So that's exactly your question there. So this is not good. If you see this, you're probably going to be encouraged to go back and retrain the neural network so that you could increase epsilons without hitting the fact that, you know, now you verify exactly 0% of epsilon balls. So for all these reasons, you do need to have training as part of your verification. And funnily enough, this need to train with certain property in mind was realized by machine learning community much earlier than by verification community. Remember that we mentioned this publication in 2013 there about these panda networks that were adversarially vulnerable. And then since 2013 up until now, you go to any main machine learning conference, and the bulk of papers, maybe 50% of papers, will be exactly how you retrain neural networks to be epsilon ball robust. So it is it's one of the major problems in machine learning nowadays. So you're talking about thousands of papers. If you really wanted to understand how to train my neural network robust, you're probably talking about reading tens of thousands of papers. And this is kind of it, and that's ongoing. So when verification community came here in 4 years' time, obviously the first verifiers had nothing to do with training. But as vehicle developers, when we came to this 3 years ago, we could no longer ignore that all this work by machine learning community is being done. So we need to somehow connect these two streams of work, verification and pure machine learning, under the hood of the single tool. So let's relax first and just think about it simply. Training generally, right, depends on data, depends on loss functions, and perhaps other parameters like shapes of the functions. So this is simple. You could imagine that, of course, machine learning community tried all these 3 paths in terms of making their neural network robust. So first of all, and this is the simplest, you augment your data set. So you get the results, my neural network is not particularly robust. You say, I changed the data set. So I will use this D for the training data set. X and Y would stand for inputs and outputs of my neural network. And so prior to training, I generate new training data samples close to existing data samples and label them with the same output as the original data. So I'm generating more images in the epsilon ball of X1 and label them as Y1. Generate more images in the epsilon ball of Xn and label them as Yn, and then give this huge file to the neural network and hope it will make sense of it. So if you think about your neural network trying to classify data manifold, suppose into 2 classes, and that's your data manifold. So X is for your original images, and now I'm generating more data because I'm sampling also in these epsilon balls of my original images. Okay, well, there is one problem with this. Suppose my original decision line was lying somewhere here, as you see. And then I started to blindly, because I don't know in advance, I start blindly sampling around my x's and always assigning the data same class as my x. Then you can see that suddenly I start my neural network, encourage it to learn something different from what the decision line is giving me, right? So this x should have been in a purple class, but by sampling here in this region, and giving them the same label as x, I'm encouraging neural network to learn a different decision line. And that may or may not be a good thing, depending what the original data was about. So that was a not good thing. And you could see that there can be even worse cases, right? My original data could have had some x's there that are actually so close that the epsilon balls intersect. And then if I do data augmentation, I will actually be given conflicting labels to the images in that red region, which will even further confuse my neural network. So that's data augmentation is great because it's so simple, and it's not so good from geometric point of view. And then machine learning community said, well, the solution, nice solution to this would be to ensure that we rather encourage neural network to understand the notion of gradient, right? We want to say that if something is in this epsilon ball, then we want this to be not so much different, its classification probability, or the number you get as a classification number, to be close enough to the initial x. But I don't want to say which class it is. It's going to be in a gradient style. Well, and how to do it? Because data sets, in a data set, you cannot say, this thing from the epsilon ball, I'm giving it the probability 0.3, because data is deterministic, right? Anything you say, this is in a class this, and this is in a class this. Data sets, they don't assume probabilistic assignment of images to classes. So in order to get this gradient thinking about your data, you have to somehow change the mode of your training of a neural net. And so let's think about loss functions generally. How many people know about loss functions from machine learning? Okay, well, few people know about loss functions. If you don't know anything about loss functions, that's your chance to learn about them. That's all you have to know about loss functions on one slide. You're given a data set D, right, which has inputs and outputs. You have, of course, your neural network. And notice now I'm actually annotating this neural network F with theta, because theta will be the learning parameters, and it will be important for us to bring that parameter in the picture. But nothing changed. It's just a neural network. I simply prefer to say, well, these are exactly the parameters of the neural net that will change during training. The type of the neural network as it was, And so the loss function, so let's have a look at the definition. It has this type from Rn to Rm to R. So what it does, it computes a penalty proportional to the difference between the output of f theta on a training input x, therefore the first type is Rn, and the desired output y, therefore the second type here is Rm. Okay, and then the result is just one real number, which is the penalty number. For example, this is the most famous loss function that's used in machine learning, most common. That's cross entropy. Cross entropy assumes that your neural network is from real numbers to the vectors between 0 and 1. And the cross entropy is defined. So I'm putting this definition just for us to map this type, general type of loss function, to something that is classic in machine learning. So loss function takes x and y of the type Rn and Rm. And then it gives us, well, a formula that will eventually give us a real number. But, well, yi here is the true probability for class I. F theta xi is the probability for class I as predicted by f theta when applied to xi. And after that, you take a log, multiply, and then take a sum over all of your classes. OK? So they are not very complicated things, those loss functions. Right, what gradient descent does, and again, gradient descent is the most common algorithm in machine learning. It minimizes the loss Lx hat y between the predicted value, f theta x hat, and the true value y for each entry x hat y in my data set. So the way it does it, I'm not going to go into the actual algorithm of gradient descent because it's not relevant to our discussion here. But in terms of optimization problem, gradient descent solves this optimization problem. So this is a standard machine learning notation, the way they describe it, because it hides quite a few details that are irrelevant and highlights the ones that are relevant. So I'm training in this. This should be read like this. The things that I'm optimizing, the parameters I'm optimizing, are sitting here in theta. And when optimizing theta, I will be minimizing the value. Remember, loss function gives me the value, which is just one number. I'm minimizing that number that the loss function gives me. So this is what the classical gradient descent does. And this is for, before we talk about robustness, so this is a standard training. And in machine learning community, then they said, well, and if we wanted to encourage robustness of neural networks, we're talking about adversarial training. And on adversarial training, we instead minimize the loss. It will again be a minimization of loss, but with respect to the worst case perturbation for each sample in D. Because remember, we were talking, even in verification scenario, we were saying, OK, let's find this adversarial example within epsilon ball, and if we found it, that's the culprit. So this idea is still here, but it's cast in machine learning terms. So if that was our learning objective here at the top, minimization of loss functions, it gets transformed. Well, this mean theta is still there because gradient descent is still gradient descent. It's the same algorithm. But inside of it, we do something different. So now I'm putting this max. I'm maximizing the loss. I'm trying to find x here that is in the epsilon ball of x hat that maximizes my loss. And then I train to minimize the loss function with respect to this worst case perturbation. And this is the standard adversarial training. This is what was happening before verification people came. So machine learning people can work this out without us. They don't need us to do this. This is kind of a standard stuff for machine learning community. And I'm having their new RIPS 2018 tutorial for those people who want to have a look. It's very simply explained there. And you can optimize for other things. So this is not epsilon ball robustness the way you saw it. It's Lipschitz robustness. And there are more sophisticated approaches to property-driven training. You can tailor neural network architectures. You can tailor activation functions. You can include probabilistic or deterministic solvers inside of layers of neural networks. They're actually some very exotic solutions. But the more exotic the solution is, the less general it usually is. So I'm giving that paper to you in case you wanted to see a survey of methods available. But we are, in vehicle, we are only interested in manipulation of loss functions, as I explained to you. So we'll be looking into inspiration that comes from adversarial training. So we are looking at it from optimization perspective. OK, so great. So what did we learn in the last 5-10 minutes? We learned that machine learning community knows how to make neural networks more robust. Congratulations to them. And maybe even if they are more robust, maybe some of them will even be verifiable. We just could hope for that. We could just say, let's not touch this stuff. I have machine learning neighbor in my office. He will just train neural network more robust. I will not look under the hood. We could do this, but unfortunately, we designed vehicle. And for a vehicle designer, it's impossible to say such thing because we have the issues of interoperability and interpretability. So for us, it's not good enough that some neighbor just trains it in any way he likes, and then I hope that by magic it becomes more robust. We want training to be encouraged by exactly the property we state in vehicle specification, and not by any imaginary other property that they want. Recall the epsilon ball robustness. We were defining it that for any image in the epsilon ball, we want this image output of the image to be robust. It happens that when we started to study whether we can actually trust machine learning people in this instead of doing dirty work ourselves, it happened that different styles of learning that we found in machine learning literature encouraged different definitions of robustness. So this argmax FXI is what we were proving. Luca was proving this sort of robustness. So data augmentation actually encourages the kind of robustness that Luca proved in his lecture. But adversarial training encourages a different one. When you compare the output of your ideal image and the output of the image for your epsilon ball, and the difference between them should be less than delta. There are other methods that encourage Lipschitz continuity. This one that we asked to do as an exercise, output should be greater than eta, is encouraged yet by one other paper. So it turned out that you could be naive and say, who cares, epsilon ball robustness is all the same. But then you can simply choose the wrong training method, and you're hoping that it will help your robustness. But actually, your robustness completely deviates from the robustness that's implicitly encouraged by certain training methods. So we found out other things, that one kind of robustness does not necessarily imply another. So I can be more robust in one definition of robustness and even less robust or just incomparably robust according to the other definition. It's easy to get it wrong, and while optimizing in training terms for one kind of robustness, achieve little in verification success rates because your definition of robustness is different in VCL file. And a very good example is that in majority of machine learning and verification papers, adversarial robustness is used for training. This is the one where we optimized loss with respect to the worst perturbation. Well, it encourages what's called standard robustness of networks. But when you go to Marabou, they actually verify for classification robustness. There is something dangling there. Do you see that there is?
Yeah, that's just
okay. Okay, that's fine. Okay. And so we show that these two types of robustness are not in any relation. You can generally increase one, and the other does not increase. So that's again one of those bugs that you find when you actually try to get a principled approach to interoperability issue. So when people did not notice this until we discovered this. Why? Because they didn't have a tool in which you could have the single spec both for training and for verification. And then what to do with properties that are not epsilon ball robustness? Because out of the box machine learning methods like PGD only work with epsilon balls, but we can have ACOS XU or who knows what. And for them, we don't have standard machine learning methods at all. So essentially, what we are looking for is to have a verifier, suppose Marabou, have a neural network, suppose in Python, and have a specification and vehicle here in the middle. And then we want everything to evolve around the same specification, not to have any deviation between them. And this will, of course, encourage our interoperability. So we are going now into this part of vehicle, training and counterexample search. So what happens there? We'll say that vehicle's formula is this. Property-driven training is differentiable logic plus PGD optimization. And just to go back, property-driven because everything in the vehicle should be governed by this top-level property in your VCL file. So everything, verification, training, integration, everything should be subordinate to the property you defined once and for always. So what is differentiable logic? There could be another lecture on differentiable logics, and I don't want to do it. You can always look up. So I can only give you a very quick example. What differentiable logics are interested in, you have some logical syntax. Let's, for a second, imagine that this is this simple one. I have comparison between two vectors. I have which form propositions. Propositions can be joined by conjunction and implication. And depending which differentiable logic you use, this one is Gödel fuzzy logic. You have a certain translation of your logical syntax here into the language of loss functions, essentially. So for example, if I wanted to translate A1 is less than A2, I have this formula 1 minus maximum A1 minus A2 divided by A1 plus A2 and 0, so maximum of these two values. And is a minimum, implication is a maximum of 1 minus translation of P1 and translation of P2. Something along these lines. There are different ways to translate this, but let's take this as an example. Well, remember, this is one of our definitions of robustness that says subtract outputs of your ideal one from the one from epsilon ball, and that should be less than delta. Well, that would be, for example, a translation of that as a loss function. So we get rid of the logical syntax, and we get something that could be parsed by your Python code as a loss function. There are different existing differentiable logics. And yeah, you can look up. I'm leaving the slides there. There's really no time to go into details. And one of the papers that looks and compares them all is by my student Natalia. Her picture you saw at the start of this talk. So we tried in this paper to somehow conceptualize a little bit what happens in this domain of differentiable logics. And it has a bit of vehicle syntax as well, if you already like it. But basically, one of the messages of paper by Natalia and other co-authors is that it's actually quite deep when you start looking at it. So on the top here, you see some of the logics that were proposed in the literature. And they can have geometric and logical properties. For geometric, for example, smoothness. Shadow lifting is a form of monotonicity. So if you increase the value of one conjunct, the whole conjunction should be increased in the value, something like this. So, and some of them have those properties holding or not. And then there are some logical ones like idempotence, commutativity, and even soundness. So there is actually, it does matter which logic you choose. This is just more or less a quick detour saying that you need to be somewhat mindful which logic you choose, and vehicle implements them all. So for a vehicle, it's very easy to just give the user a choice. So we at the moment don't make any preference. We just say the user will tell me for which logic I want to compile loss function. Okay, property-driven training equals differentiable logic plus optimization. We've covered differentiable logic. How about optimization? Recall we just considered standard projected gradient descent, which minimized the loss with respect to the worst case perturbation. And we're talking about optimizing for this learning objective. Okay, so what then do we need to do with vehicle about this? In vehicle, we're assuming that generally we have a property of this shape. For all x, precondition x, p implies postcondition s. So we replace this one, this learning objective that's standard in machine learning literature, with our own, which is not very different. Then we keep the top out minimization objective because we're going to be using standard gradient descent. So the training algorithm will be standard, therefore it will always be minimizing the loss at the end of the day. But we look inside, we look at this inner maximization there. And we need to be now a little bit thoughtful as to what we do. Well, first of all, since I have my differentiable logics, I can just use translation of differentiable logics and get a loss function out of this Sx. And this is what this part is saying. And then what I want to do is to find the maximum loss for x that I sample from a hypercube that I get depending on what my preconditions are. I know it's a little bit complicated, but it's actually incredibly natural. So I'll show you that on examples. This is Ekaterina that we've seen, right? So the shape in which I'll be searching for the worst perturbation will be given to me by the normalized vector bounds as given by the Ekaterina engineer here. Those 5 lines give me the bounds within which I'll be searching for the worst perturbation. Of course, they are formulated here now by engineers like that, but recall that in Ekaterina networks, every x is sampled from the vector space where vectors have size 5. So, right, and then this is my HPX, the shape within I find adversarial examples, and my loss function will be given by, say, Gödel translation of the postcondition, which was not minimal score clear of conflict. So this can be easily automatically compiled by Vehicle into a loss function LSX and a sampler within HPX. Okay, so there can be degenerate cases, of course. Instead of for all x px sx, you can just have for all x sx, not to have any precondition at all. In this case, this formula that we are looking to fill in, well, LSX will be given by the same translation that you have, but you wonder what happens with HPX. Well, because there is no real p, you will be searching for the whole of the domain of your variable x. And usually, whatever you do, there is some kind of normalization on variables anyway. So, for example, if you normalize between 0s and 1s, you'll be looking for the worst perturbation within these bounds, 0s and 1s. And that is standard robustness, epsilon ball robustness. We say within the epsilon ball we want to have this objective working. Well, then my HPX within which I'm searching for adversarial example will be the epsilon cube around x, defined here. Oh, I'm saying cube rather than epsilon ball because I'm assuming L infinity distance. If I was using Euclidean distance, I'd be calling it epsilon ball. And then my translation for this post condition will be given just as we computed a few slides ago. For example, using Gödel DL. Okay. And so what happens in Vehicle? You use the same specification, same VCL file as for verification. You need a TensorFlow version of your network, right, if you want to train. We only gave you Onyx, but Onyx is just a static snapshot of a network that you use for verification. You need to have a TensorFlow version of that same network. Otherwise, your TensorFlow library is not going to run Onyx for training. You need, well, you will be given by the Vehicle developers the Python template. And in that template, you call the Vehicle specification and the network. And then you run your Python script, given as template, and then you, well, with some filling in. So the loss function is automatically generated from the VCL file. So that will be done for you. The hypershape HPX is currently provided by the user, but we hope to be able to finally, at some point, to compile that down automatically. It is definitely possible. And then you just call the standard PGD, projected gradient descent algorithm that you can find in any Python library to find counterexamples within that shape and native stochastic gradient descent training from TensorFlow to minimize the loss LSX. So basically, you tailor compilation from the Vehicle file towards the state-of-the-art practices in machine learning to the standard optimization methods that already tested and tried in machine learning community. And yeah, and all of this allows you to solve this optimization problem that doesn't look that different from what machine learning people already know, except for it gives you guarantees that this loss function and that shape are compiled directly from your specification file and not from anywhere else. Okay, so you have seen now training and counterexample search. And this now encourages interoperability. So we're now controlling, there's a single control center to control both verification and training, and that's our property spec that's been typed and cleaned of all errors. Next thing that you will see, and Matthew will give you the demo, will be the final thing that you need to know about vehicle, and that's integration into larger systems. So once we cover that, we'll be done with all the theoretical blocks of vehicle. And I think I should give the stage to Matthew.
Cool. So what you've seen so far in vehicle is reasoning about a neural network in isolation, one neural network, whether it's training that neural network or whether it's trying to verify that neural network. But neural networks are rarely used in isolation. Usually they're part of a larger piece of software that uses the neural networks to form some subclass. And we are interested in the scenarios about when the correctness of that larger software system depends on the correctness of the neural network. And as an example, we're going to see one more example. We've seen lots of examples of neural network replication conditions. We're going to look at an autonomous car traveling along a road. And we're going to have a really simple system. Just as an example, you can make it more complicated if you like, but just for the moment, there's a car traveling along a straight road, so from left to right. There is a crosswind blowing up across the road, which the car has to steer against. There are obstacles on the road that the car has to avoid, and the car would like, the aim of the system is for the car to stay on the road. It can take sensor readings of where it is on the road. There might be some noise in those sensor readings, so it doesn't have a perfect idea where it is on the road, but it approximately knows where it is. And the sensor readings it can access the sensor reading, and it can access the last couple of sensor readings that it's got. And what you would like to prove, the safety property of this entire system, is that you would like to prove no matter what sequence of the way the wind blows, whether it's really strong, whether it's weak, whether it's strong then weak, no matter what noise is on the sensor readings up until a certain bound, then the car will always remain on the road. So that is very much a temporal property. It's for all tidings t and for all sensible environmental measurements, then the car will always remain on the road at time t. So you can see maybe we've got the theorem. We've got this theorem 1 that we would like to prove about the system, and we're assuming the wind speed can shift by no more than 1 meter per second, and that the sensor is never off by more than 0.25 meters, then the car will never leave the road. So that's what we'd like to prove. And you can imagine wanting to train a reinforcement learning algorithm to do this, to avoid the obstacles while staying on the road. So this controller for our neural network, this controller for our car is actually going to be a neural network. And we would like to verify that the car never goes off the road. Now, obviously, from what you've seen in the vehicle syntax, it's very clear that vehicle is not designed to reason about arbitrary programs or arbitrary models in this way. It's very much a language for writing specification conditions for neural networks. So we can't do this, we can't prove the overall theorem that we would like in vehicle itself. So what do we do instead? Well, we can export a vehicle specification to an interactive theorem prover. Now, I think you've got some talks tomorrow about Isabel, which is another interactive theorem prover, and I think Jörg mentioned yesterday about POP and lean and Isabel as well. These are all interactive improvers. We connect to a slightly different one called AGDA, which is similar, has a few differences to the others, but is broadly very similar. General purpose theorem improver. You can write programs and proofs all in the same language. So we can formalize this model of the car in AGDA. So we can say we have a state of the system, which is the current wind speed, its current position, its velocity, the velocity of the car, what its sensor reading currently is. And we can say we have observations, which are instantaneous, how much the wind is shifting at this point in time, and what the current error on the sensor reading is. And then we can formulate a model, as you can say, initial state. You can say, here we go, with initial state, we have a controller. We can say what the net state is, given an observation, and the current state. So the new wind speed is the old wind speed plus the wind shift. The new position is the old position plus the velocity plus the new wind speed. So the wind kind of pushes you off the road. The new sensor reading is the new position plus whatever your sensor error of your observation is. And your new velocity is the old velocity plus whatever your controller is telling you to do. So this is a very simple model of what we've got. And then given a list of observations, we can compute your final state simply by folding over the next state function, start something interesting. And we can formalize various things like the car is on the road, into a position of in state S, the position in S is less than the road width. So we can formalize various things, but crucially we can formulate, right down the bottom of this file, we can prove in AGDA, we can state in AGDA our final theorem that we would like, which is that for all valid observations, series of observations x's, then the final state after you apply that sequence of observations is you're on the road in that state. So the question is, what do we need to prove about our controller in order to get its theorem to go through? And if we store it up, you can see that the actual proof is relatively complicated, lots of arithmetic manipulation. But the crucial lemma that we find that we need in order to prove this is that if x is the current sensor reading and y is the previous sensor reading in time, and if the absolute value of x has to be less than or equal to the road width plus the max sensor error. If the maximum value of x is less than or equal to the road width plus the max sensor error, as is the sensor reading from previous time step, then in that case we would really like the output of the controller plus 2 times the current sensor reading minus the previous sensor reading has got to be strictly less than the road width minus the max wind shift minus 3 times the max sensor error. And if we can prove this lemma, then this proof goes through and we know that it's true. So this proof is a temporal property, it's about sequence of all valid observations. This proof is much simpler. This proof is about one instantaneous application of the controller, about bounds on its inputs and bounds on its outputs. So this is amenable to proving in vehicle. So we have another example. So we can code up this limited property in vehicle. So this is the vehicle spec version of this lemma with, I should note, the appropriate values filled in for road width and max sensor error. So we've substituted numbers in here. We could have that unsubstituted, which is easier. So an input is safe is if by every element of it is between these sounds, and the output is safe if the output of the controller plus 2 times the current sensor reading minus the previous sensor reading is between minus 1.25 and 1.25. And the property that we would like is that for any safe x, then any safe inputs x, then output of the network is same. And we have a little neural network controller on X here. So we have our network. And what we can do is that we can verify. We can verify this spec as before. So we call vehicle.verify with the specification, the network, pointing to the network, the verify arrow. And crucially, we pass this extra argument called cache. And that tells vehicle to output the result, store the output of the verification, so whether it's verified or not. So if we run this, we can install 2 queries, and it's a very simple network. It's only got 2 inputs, so it's very quick. And it says there's proof no counterexamples. And crucially, we now have this cache object, this verification cache object, which stores the result of it. So we can then ask vehicle to export that cache to Agda. So vehicle, and we use the export mode, and we say targets Agda, we give it onto the cache, and we make the output file, and we give it that tell it where to output the output. Cool. Oops. Okay, so we've outputted the output file into our Agda proof folder, which is here. So we generate Agda, an Agda version of the specification, and then the proof of this in Agda is a macro called check specification that calls back to the vehicle and checks the verification cache that we made to check that the proof still holds. And then in our safety proof, we can import the generated specification. So this is the folder that this is the file that we just generated, and we can use it to fill in this hole. And crucially, you see we have vehicles like here. This is the proof that we generated. And the verification cache holds the hashes of all the resources and that we use to compile the specification. So the neural networks and data sets, so that when we check, when Agda says, does this property hold, the vehicle goes away and rehashes the resources, so the network sees that the network doesn't change, and it says, yes, this proof is still valid. So in that way, we're really linking in our interactive theorem prover. We may not be representing the neural network directly in the interactive theorem prover, but we're actually really linking to the deployed object, the actual object that runs on the system. So that's the way in which you can export to ITPs. We've got Agda support at the moment. Support for other ITPs, your favorite ITP shouldn't be too hard to add. Yes. So that's the hope. We've got the simple proof working in Agda. We're hoping to do some more complicated things in the near future. And we're very much open to ideas. If people have ideas about proofs of systems that use neural networks, would be very interesting with that.
Thanks a lot, Matthew. So should we give a clap? Luca will now finish the tutorial with a few slides of conclusions, but are there any quick questions to Matthew? Because it's unlikely we're going to have a long question session at the end.
So the original work was some obstacles. So the original problem was some Richmond Boyd. Did you consider Richmond Boyd? How you consider that?
Sorry, can you repeat the second word? Reachable. The original problem was.
So your property was just safety, and you can translate that into just static evaluation of the neural network. And so I want to know how the system works if you have some sort of network property. So, for example, Richard Boyd.
Reachability. So what would happen if you wanted to do reachability? Then there's a feedback loop between you need to attach some sort of other automatic solver that does the iterative refinement of the reachability bounds. And what you would need is then to parameterize your vehicle specification by the current, by what the current bounds are, and then you repeatedly call re-verify, I guess, on the vehicle specification with updated bounds for every iteration, every time you want to check that your updated bounds and your network really does satisfy that. We have not experimented with such a thing, but it should be possible.
And that's exactly the point where where we say we want collaborators. So if people want to hack into this, we'd be very happy to look into your examples. I think we cannot go into many questions. Matthew, thanks a lot for joining. I will catch up later today. And that was a fantastic demo. Thanks again.
All right, so I am just going to finish off with some slides on application areas. We don't have a lot of time, so we'll be going over a lot of potential topics quite quickly. Please come see me at lunch and let's talk about this more. Effectively, what we've shown you so far is a small subset of what you can do with neural network verification. We've looked at images, but you might think, yeah, so what's the big deal? I can get true image digits. Doesn't really matter. So I'm going to go over some practical examples of things I've been working on, the vehicle team has been working on, and then some real-world problems we're facing with. So all of you were familiar with the panda gibbon, and we've shown you a few times. Well, this is a real attack. Turns out if you can put a little sticky note on a stop sign, all of a sudden this stop sign is a 70 miles per hour sign. Now, autonomous vehicles are currently being deployed in the US, in London, etc. Imagine what that little nifty attack could do and the impact of that. So verification of robustness, even such a simple property as this, has huge real-world impact. So this is something that could actually be verified and actually look like. Another area of interest that actually we've been looking at with the vehicle team quite a bit, and we have a preprint out on, is natural language processing. So I think you're familiar with ChatGPT. And let me preempt this by saying we're never, ever, ever verifying 70 billion parameters. However, ChatGPT does have certain filters that we can verify. And I'll explain this in a lot more detail if you talk to me later. But the basic idea is this. So we want the robot or the chat agent to be able to always respond yes to are you a robot. And I'll show you in a second, this has actually become legislation in Europe and California, which is a very, very, very difficult problem. How on earth are you going to formally verify that a huge language model is going to always say yes to being a robot? And we've shown some perturbations in images. Well, these are what the perturbation looks like in text. So spelling mistakes, random changes of characters, words that all of a sudden change, or all of sentences that actually can be changed. And all of these need to be able to, are valid perturbations and valid ways of training a robot. So actually being able to actually characterize a domain or a geometric shape around this perturbation allows us to play the same trick then with the epsilon cubes, or epsilon rectangles in this case, you can ask me later why, to verify every single possible way of saying this. And this is an area that we've done quite a little bit of investigation on. We actually have, this is the motivation for a thing, this huge legislation, that people have the right to know if they're interacting with a machine, which, you know, in practice seems like a very nice thing. Concretely, it's very, 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 very difficult to mathematically formalize. But yeah, another example, so this is code, should be a little bit familiar to you. This was a paper that came out a couple of years ago at S&P. So this showed that by just adding random lines to your code with random libraries, all of a sudden the malware detection on your Android phone stopped working. So what you install an app from Google Store, Apple Pay, it runs malware analysis. So it checks the code and makes sure that it's not malware. That's great, right? However, if I start taking a piece of malware, add completely nice libraries, random functions that do nothing, etc., which systematically is exactly the same malware, all of a sudden they were able to bypass this and it ran no problem. So this is a huge issue, and this is something we need to be able to verify. And again, this is just an example. You can ask me any more details. There's a nice paper on this. Finally, this is the last example. This is something I've been working on recently. This is intrusion detection. This slide is really ugly, don't worry about it. But the reason why I brought this up is, for those unfamiliar, intrusion detection, you have some network traffic, you put a monitor in the middle, checks all the network packets, make sure there are no attacks, very simply. But this is what the features look like. These are all numerical values that are inputted to the intrusion detection system. All of a sudden, we have a nice little situation where the input space and problem space are identical, which is very, very valuable for the neural network verification, because we don't run into this weird problem of scaling back and forth. And actually, in this example, it's quite exciting, because we're finding we might have an ability to easily check, when you make a little perturbation, the impact of it in an original problem space, which from the perspective of formally verifying something is very, very, very powerful and very interesting, because all of a sudden we can get minimum perturbation and see the effects on the original network traffic. And the attacker model here is you have an attacker intercepting the traffic, putting new packets, it's able to bypass the intrusion detection. This has been proven, it already exists, it already works, but we'll be able to formally verify that this doesn't work, which is quite exciting. This will be hopefully coming out soon. And there are tons of others. So this is a graph by Nicholas Carlini. You might be familiar with him. He's at Google. He's a big name on this kind of thing. He's showing that the number of cumulative papers is increasing exponentially. And there are several new attacks coming out pretty much every day or every security conferences. We need to start verifying this. And so coming up with a tool that is able to do this quite effectively and coming up with all these properties is very effective. And that's exactly how we envision using Vehicle. We now have a nice tool. We can run a tutorial on it. Next step is you guys coming to us, giving us some nice examples, or using these examples on the literature. So as a final thing, I wanted to bring up a couple of solutions of stuff we already have done in this area, so we're not completely behind. This is a tool a framework we prepare for natural language verification, natural language processing verification. It goes from the whole thing, from the NLP data set to formal verification. Again, this is not super, it's very complicated to explain, but it's quite nice, because then we looked at all the possible types of attacks, or the possible perturbations, and now do some nice verification on it. And this is out right now, so you can ask me about it or read the paper. Another thing that I've been working on with industry, so if you remind at the beginning, the perturbation here was the input on the inputs. Well, I was talking to some car companies who were really, really interested in this problem. They have these sensors, and they can detect everything on the road, no problem. But all of a sudden, this was Scotland, there is a bit of a problem. All of a sudden, this sign becomes a 70 miles per hour sign, etc. But they had a very good representation, understanding of what snow looked like in these things. And they could give me some nice mathematical formulas from their simulator models of saying, this is the range of values we could take. And this was the same with fog, this was the same with brightness, etc. So coming up with these mathematical representation, what is snow, what is the input snow takes, actually has some real nice real-world implications of etc. And please do come ask me this if you have any questions, because this is something I'm currently working on with a car company. So anyway, and this is the same with the thing. Anyway, just to summarize, since I see we're out of time, Vehicle here stands at the center of a bunch of potential. We can verify neural networks, we integrate with machine learning libraries, we can even interact, we can either now integrate with interactive theorem proving, as Matthew has showed you. And what I would just summarize is, so this is just a summary of everything it does, all the integration. I think this is out of date because this arrow now exists, so apologies for that. And I just want to summarize by saying Vehicle allows you to properly specify, and it's a central point for any engineer, any person who's hopefully interested in this area, or is interested in this area after talking to us today, to start here, and then we can go to pretty much anywhere you want across these application areas that I realize I've skipped over very quickly, but I'm conscious of time, etc. These are some upcoming work I'm interested in doing, or our team is interested in doing. Talk to us if you're interested in any of that. And that's all. That's our tutorial. Katya, unless you want to bring something up in particular. I know I rushed through this, but I saw we're out of time.
Because we're out of time.
Yeah.
Thanks for the organizers so much for inviting me.
Yeah.